All right, good morning everyone. I hope you had a good evening yesterday after a hard day of work. Today we're going to look at the various CAMS services and hear a little bit more about what's under the hood, what are the developments, what is the current status through the various sessions we have today. And we're starting with Johannes Fleming, talking about the global monitoring and forecast of aerosols and reactive gases.
Good morning, everybody. So I'm very happy to start off this day with a very short overview of what we do in terms of the global CAMS system for aerosols and reactive gases. This is, of course, a group effort. Many people are involved. At ECMWF, it's people from the atmospheric composition section, but also the forecast and service department to actually run these forecasts. Many of the actual model developments for aerosols and for chemistry are done by the CAMS 35 contract led by Vincent Heunen and Samuel Remy, and many people are involved here. But it's not just the developments, it's also the input data that we need to the CAMS contract on the emissions is very important for the success of what we do. And then finally, everything has to be evaluated, and we also have a specific contract about this one. So this plot has been shown yesterday. It's in a nutshell what we basically do twice a day. We use the IFS, which is the NWP forecasting system of ECMWF, which has been extended with modules to simulate chemistry and aerosols. We make forecasts over 5 days globally at a resolution about 40 kilometers. And at the beginning of each forecast at 12 and at 0, we use the data assimilation technique to improve the initial conditions of the forecast using satellite retrievals of various atmospheric composition products. So that's basically what we do. And we are here in Copernicus, so it's really important that we do make use in this way of the observations from space. This is here a table of what instruments we use for the different aerosol and reactive gas components. So it's a very long list. The ones in red are actually used right now. The ones in black are instruments or products for the various species which we currently explore. And we also have to say goodbye to some of the instruments, and most notably it's MOPIT for the CO, which has been serving for a very long time, was very important for the reanalysis, but this is now has ceased the production of data. So we focus on making sure that we can use more satellites, and in the last 3 years or so, we really were in this position to make use of these new data sets coming from the geostationary platforms, so namely GEMS for Asia, TEMPO for North America, where we have data and where we use the data already, and we all, of course, look forward to Sentinel-4, where we will have the data over Europe. Just to illustrate how this improvement in the capability to observe from space has changed, Antje Innes put together this animation. What we see here is a composite picture of the observations that are available. So in the past, we would have those polar orbiting satellites from GOM and S5P providing once-a-day observations of NO2, but now with TEMPO over North America and GEMS over Asia, we see that over these areas we have observations for much longer, which is basically the daytime conditions when we do have these observations. First tests have been run to use these data also in the data assimilation context, and then we try to, as usual, investigate using independent data to what extent we see improvements. So this is just sort of the first trial. It's not the end of what we do, but that's where we are currently. So if we look with respect to surface NO2 observations, the assimilation so far doesn't change so many things, so the scores are relatively similar. But what we are very happy to notice that we do get considerable improvement in surface ozone. So for the surface directly, the impact is very little, but because not just the surface values are changed, but also the NO2 conditions throughout the troposphere and the lower part, at least that's what we believe is happening. We see an improvement in ozone, which is shown on the right-hand side, say with the differences and the absolute bias between a run with and without the addition of the tempo data. Now, this list here is a summary of the updates that we plan. And it's very detailed, and I don't want to go into all the details. Just for everybody to note, we update our system about once a year, together with the NWP updates of ECMWF. We give these versions, we call them cycles, and we give them numbers like 50R1 and 50R2. So the next upcoming update, which has been prepared and where we do only technical checks at the moment, is 50R1. The current date of the implementation is at the end of this year, even though this may slip also a little bit, but we are not certain yet. We have several updates. Many of them are listed here. Important ones are an update of the emissions. We now switch to online BVOC emissions, and we also reviewed how we do ozone dry deposition. In terms of the data assimilation, we revised and finally tuned to optimize the background errors for the 40 VAR data assimilation. And there are many other changes. The next cycle, which come after this, is what we call a technical cycle, but it's of interest for this community because also the way we will encode our data and GRIP will change, and we will inform you in a timely way to make sure this technical change is okay for you to handle. And then in about a year's time, we expect then hopefully another scientific cycle, and some candidate updates would be to try the inversion of NO2 already, and also to change the dust representation considerably by introducing a scheme which has 6 bins rather than the 3 bins that we have now. So 3 slides now on updates, and they very often focus on the emissions, and I think it's a fair summary that to paraphrase sort of a political statement, it's the emissions stupid. So the emissions are really the most important thing, I think, and we get improvements by changing the emissions. What we see here is work that we started off with in the preparation of the CAMS reanalysis, where we also had to be quite careful in looking into the trends. So for the operational forecasting system, we just focus on the present situation. But if you want to do a reanalysis, you have to make sure that the trends that you use in this context are correct over the 20-year period. And what you see here in this plot provided by Claire, different emission data sets for SO2 over the United States, and you already see that there are considerable discrepancies here, and we found out that using the EPA emissions directly would lead to a much better descriptions of the trends rather than using the EDGAR data that were initially planned. And so we are very grateful that the CAMS emission contract put together a composite data set, which is called Mosaic, which consists of EDGAR data in all the places of the world where we don't have an alternative trustworthy emission data set, which is America, Europe, and China. So we're using this data set now, CAMS Mosaic, for both the reanalysis and for the operational system. And you see here 2 plots for SOX wet deposition and also for SO2 over North America, how this new data set improves the modeling of SO2 or SOX wet deposition fluxes. The fire emissions are very important input for us. The fire emissions are basically the main driver for variability. The fire emissions, as you know, they are observed from space. So, and when we, at the end of the year, look at anomalies of chemical species of PM2.5, we always find it's the fire emissions that describe the year-to-year variability. So fire emissions are very important. In the past, GFAS has been based entirely on MODIS, but we know MODIS comes to an end. So a lot of work has been put into this effort to make sure that GFAS also runs with VIRS emissions, making it future-proof. And on the bottom of this slide, you see two verification time series, one for PM2.5 and one for AOD, showing that this new GFAS version using VIRS leads to better results. And you have to be careful that the color scale between the two plots switches, so it's always an improvement. Online BVOC emissions. So in the past, we used emissions from inventories. Yesterday, we discussed that it's one of the anticipations or expectations towards CAMS to do better modeling of natural emissions, and maybe also this fits into this context. So we moved to an online emission scheme, and Flora Kluge could show that we have a better description now of the diurnal cycle if we directly compared with isoprene observations over the Amazon. And this plot on the right-hand side shows results specifically for the Netherlands, where we can show in this case that having online BVOC emissions, which much better respond to the changes in meteorology than in climatology, leads to a better forecast of specific ozone events over this area. So it's already here also a good improvement. Ozone tri-deposition. For a long time, we noticed that our system had a relatively high bias over North America. Surface ozone was overpredicted. We are not the only one, the only model that does this, but still we thought it's a problem. And we also realized that it's not just a summertime problem, but it's also a wintertime problem, which led to this conclusion that actually the ground resistance for the tri-deposition scheme, so not the one related to stomatals, but just sort of the deposition pathways via the ground, is an area where we can maybe do some tuning. And also, a summary of the ACME model intercomparison activity, we thought it's worthwhile just trying to reduce the ozone tri-deposition velocities by changing the parameter for the ground deposition, and we could show that this simple change of the deposition led to improved forecast over North America, as shown in the plot on the top where you see the map. So the blue and greenish points show a reduction in RMSE, and you see a time series over summer, also 50R1, with lower ozone biases than what we had previously because of this change in the tri-deposition. Now, just one word on a very, very important aspect that we also do and are busy with preparing. That's the next reanalysis, EAC5. So I think many of you are familiar with the current reanalysis, but we are preparing the production of a new data set for the same period, basically, starting in 2003. This production will happen in the next 3 years, and very important updates are, of course, recent updates to new observations that have not been used for EAC5, like Sentinel-5P. So this really provides several new products. But also our modeling system is, of course, a different one. Most notably is to mention here that we now have the full stratospheric chemistry represented, and we also have a much better description of secondary aerosols. And just to show that the modeling, so the data assimilation, of course, is just being tested, but we don't have a product, but we do model runs over this 20-plus year period already using the new model, using the new emissions, and what this plot at the bottom right-hand side shows is PM2.5 over North America, and with the model version shown here in green, this was the situation for the current or the previous reanalysis, and now we are moving to EAC5, which is the red line, which has a much better agreement with the observations, both in terms of the magnitude, but also in terms of the trend. Okay, so it gives me the chance to talk about a very important novelty that has started with the arrival of Paula Harder in our team, doing machine learning for atmospheric composition forecasting. As you know, AIFS is the machine learning-based version of the numerical weather prediction forecasting system, which is a graph neural network. And this same system has been applied to make forecasts of atmospheric composition, training on EAC4, and then also doing fine-tuning with the operational system. And when we do verification of these machine learning-based forecast of AIFS compo, we see that for most of the species that we look at, the quality, the scores are very similar to what we have in the operational system, and especially for AOD and PM2.5, the scores are already better than what we have in the operational system. So on the very bottom, on the left-hand side, you see a plot showing the performance with lead time for AOD. The gray curve, that's our operational system, and the green curve is AIFS compo. Some of you may know that our operational system suffers from biases or drifts, rather drifts in the forecast, because the analysis is sort of higher than the equilibrium of what the model wants. So in this 5-day forecast, we always have a small drift in terms of the total burden, but because the ML model is based on analysis, this drift does not occur anymore, and that's why the green curve, as you can see here in this plot, is really flat and doesn't show this drift in terms of the bias. And just to prove the point, what Florian made yesterday, things are moving so fast, the plot that was shown yesterday by Lawrence is already superseded by this plot. Sorry. On top is also another application which is very interesting. That's sort of forecasting the ozone hole. What is seen here shown here for 25 is in blue the curve of the reanalysis. Basically, that's the observations of the minimum of the total column over Antarctica, which is an indicator of the ozone hole. And then in blue, you have the operational forecast, and then the two ML versions for the 5-day and the 10-day forecast are shown in red and yellow. They are not as good yet, but this will change. But it's really worth mentioning that the computational cost of this ML forecast is so much cheaper. Basically, it takes a second to execute this forecast, whereas when we use AIFS on a supercomputer, it takes sort of half an hour for a 5-day forecast. We use many sort of resources. So it's really very cheap, and we are very excited to look into this. And with this, I want to finish if I have to. I have a couple of more slides, but maybe that's a good point to close. Thank you.
Yes, sorry, Johannes, but we need to move on. I'm also deferring questions to the coffee break in the interest of time now.
Yeah, I had a question about this use of NOx emission inversion in the future, maybe for next year. And I was wondering if it was designed to be more like an intermediate step in the production, or if it might become a product in the future. Some of the regional models may want to experiment with that, even if not in the operational production, but it could be relevant for regional models also to use. And more specifically, that would be very relevant for policy users. In the presentation we had from DGM a couple of days ago, we highlighted the contribution of CAMS in the Ambient Air Quality Directive. That's ongoing, but the future for us, it's the National Emission Ceiling Directive and the contribution that CAMS could do in that context. So any information that you may have on NOx totals would be very relevant for European users.
Thank you for this question. Our initial attempt will not directly target sort of to develop a new product, which would be the update of the emissions. What we have in mind, given that it works, is just to sort of optimize the emissions on the day for a particular, based on the observations, and then use the optimized emissions for the forecast. But at the next iteration, we would basically start again from the same starting point, using the official emissions and try to optimize them. Though there is no sort of cycling of emissions or updates possible yet. That's development for the future, and also, yeah. But of course, we will look at the differences, and if we find anything systematic, then of course it would be interesting for the inventories. If it's just noise going in all directions, then it's yeah, a different type of information. Yeah, thank you.
Any other questions? One there.
Hi, here Jorge Lesaca from DLR. As you know, we are doing the validation of IFS compo for the radiation, solar radiation part. When I talk with many users, they always ask me why the lower resolution is special resolution from the IFS compo compared to the IFS operational forecast. So I just wanted to know if there is some thinking going on doing the same resolution of IFS high resolution, or is there no plan on going that direction to answer this type of users?
The main reason why we run it on a 40 kilometer rather than a 9 kilometer resolution is the computational cost. But we also did specific sort of tests running it at higher resolution, and we could not find going up to 9 kilometers a better agreement with observations, basically. Of course, it may depend on how you look at it and what you are after, but we did not see this breakthrough sort of in terms of the scientific performance that we would say, okay, let's do it despite the fact that it's very expensive. But with machine learning, maybe this cost argument is not there anymore and things can be done, but that's for the more distant future.
Sorry, we're now moving on because the presentation is on the screen again. So Henk, if you would be willing to take the floor and talk about the global evaluation and quality control efforts within CAMS.
Okay, good morning. So I don't see it on my screen here. Okay, I will talk about the global evaluation and quality control activity within CAMS. And I also made a subtitle, what we do and how we innovate. So that's basically also a summary or an outline of my talk. So I will start with giving you just an overview of the activity itself, but then I'll also discuss the innovations that we made more recently and also plan for the future. It's not my work, but I'm representing here quite a large group. So we have 12 partners and some 25 people involved in the activity. So it's really on behalf of those people that I give this talk. Oops, does it work? Okay, so what is EQC doing? Well, the main aim is to compare the CAMS global outputs, which are generated at ECMWF, with all good quality observations that we have available. And that is quite a wide range of observations and different types of observations. So a lot of observations come from the surface. So we have ground-based stations. For instance, we have various air quality monitoring networks all over the globe. But also very interesting remote sensing observations happening from the surface. For instance, you have this spectacular LiDAR sensing picture there on the bottom. But then there are also all kinds of airborne observations which give information about concentrations above the surface, like the ozone sondes, the balloons, and also routine aircraft observations that we take into account in the activity. And then, last but not least, also certainly we look at the satellite observations. So we make use of data that's provided by major networks that you can see there. So we have the GAW, so the WMO GAW is providing a lot of good data at the surface. ICOS for greenhouse gases, IAGOS aircraft campaign data, routine measurements from aircraft, NDAC, the global network on atmospheric composition change, ACTRIS. Aeronet is a key network for us for aerosols, and also the various air quality networks all over the globe to monitor air quality, air pollution, and EEA for Europe, but we also look at the Chinese and the North American networks and other networks over the globe. What's quite important is we do this evaluation on sort of a real-time basis, and we basically have a cutoff time of 1 month, so we really want the data to be there within a month so that we can use it for this activity. So what do we look at? We look at reactive gases, ozone, CO, NO2, formaldehyde, SO2. More recently, as Johannes explained, we have this full stratosphere chemistry. So we also do the evaluation of the stratosphere composition. For aerosols, we look at AOD, angstrom exponent, so size distribution indicator, PM10, PM2.5 at the surface, air quality related quantities. For we also have an activity on greenhouse gases, so we look at CO2 and methane. And what I want to stress here also, we have a focus on those species also which are also assimilated, so that we can check also how much extra benefit you get from the assimilation. And in total, we have something like 65 observational data sets that we work with. And that explains also why we have so many partners, because these partners have experience and expertise in these different data sets. Okay. Now it's stopping. It's going a bit too fast. So what do we produce? One thing that we produce is a series of validation reports. What we do is we update these reports every 3 months, so it's quite an intense activity to do that. The validation reports are very comprehensive with many pages. We are now working on the MAM 2025 report, which is almost ready and will be available quite soon. So every 3 months we have a new report. But we also monitor the reanalysis, which you can see in the second. And there we have yearly updates of a full report covering the full reanalysis. But apart from that, we also look at the quality of the latest extensions to the reanalysis. So we have these 3 monthly quick looks that we provide to ECMWF about how the reanalysis is performing for the latest months. Apart from this, we also look at these upgrades, which were discussed by Johannes also. So cycle 50 is the next one, and we will be involved in the evaluation of that. And we really want to make sure that this new upgrade is not degrading the performance of the system. So apart from these validation reports, we also have online information, and we have a very rich data set available online on the comparisons that we make. So we have developed 2 evaluation servers. The first one is the global evaluation server, which is really focusing on the near-real-time products of CAMS. And that's giving a very rich and flexible source of intercomparisons, including statistics and also overview plots. It's developed by S&T. So Sander Niemeyer, who is here in the audience, is largely responsible for this. And yeah, a couple of examples here. It's a bit annoying, it's not on the screen. So what you see here is that we also support, we also support comparisons with satellite data. So we have maps where we report the difference between the satellite data and the CAMS forecasts. Then different examples, ozone profiles in the top from the IAGOS. So that's quite interesting. So you see the altitude versus time series here, and you can see how that's progressing over time. It's clearly a lot of time series, for instance, CO here. This is the tropospheric column, but also a lot of time series at the surface, clearly, like PM2.5 here on the bottom. And also overview plots where we have sort of latitude, different stations versus time, and you can see how the bias is developing over time. We have developed the second server. Sorry. We call that the global EQC server, and that has been developed by Met Norway. And it's really, this one has a very nice a very powerful interactive interface. It's basically one screen which you get, and then you can, when you hover over it, you will get all kinds of detailed time series plots, but a lot of overview statistics as well. So I really invite you to have a look at both servers and explore what you can get. So for instance, if you're interested in the performance in your own country, you can really use these servers to get the information close to home, let's say, if that's of interest, and check how things are doing and how things are progressing over time. Okay. Another thing that we do in the validation reports is that we also report case studies. And here you have a collage of different case studies. So let's go through it. So on the left, we have fires in Portugal. And there you can see that CAMS is really describing the transport of the, in this case, it's the aerosols which are produced by the fires. But there's also an underestimate of the intensity, as you can see. Below that, we have quite unique fires in Tasmania, which happened early this year. And again, you can see, for instance, for formaldehyde, that CAMS is doing quite a nice job in timing and location, maybe a bit underestimating, again, the intensity. Then we also look at dust episodes, clearly. So in the center bottom, you see this big event happening over the Sahara, being transported to the Americas. And you see how CAMS is comparing to this BDAS dust product. But we also look at LiDARs and surface observations to check how the CAMS is performing for this event. We also look at volcanoes, that's on the top. So in the last report, we have a couple of volcano eruptions over Indonesia, the region around Indonesia, and we are checking how well the plumes and intensity is covered by CAMS there. Another interesting fire case is on the right, where we have the Iagos flights, so we have the ascents and descents at the airports, but also the cruise data. So we see that signatures from fires that happened in South America are present in the boundary layer, and CAMS is doing quite a nice job there. But also we see at cruise altitude, we see these elevations, and again, we see that CAMS is capturing those, but not to the full extent, so it's a bit underestimating the intensities there. And last, we also look at air pollution episodes, so high ozone events, and that's shown in the bottom here. So there were a couple of events last year over France with very high temperatures, and you see that the ozone is really peaking at those events, and we are checking. So again, CAMS Global is capturing the peaks, but underestimating the real ozone values that you have during those peaks. Another thing that we do is we are constantly looking for new observations, and we are extending our observations database, and that's shown here. So I already mentioned we have air quality data for America, Europe, and China. That's sort of the three basic data sets we look at. But the Global South is something that's not well captured, and we are really looking if we can make use of data. And one thing that we've added is data from Chile, which you see on the top. And that's now routinely used, but also exploring data from Brazil or Colombia in South America. But then also looking at Asia, so extending to Taiwan, Japan, and South Korea. Apart from that, we also make use of data from aircraft campaigns, so they are more incidental, so it's not long time records. But it's very useful for the evaluation of the reanalysis especially. And of course, the new upcoming satellite data. Okay, yeah, I want to do this a little bit quickly. I'm sorry, I cannot have the screen here. So I have to read it by myself as well. Yeah, we just started this CAMS 282 bis project in July, so the follow-up of the CAMS 282. And we are proposing a lot of extensions, especially we are really looking at this new generation of satellite data. So looking at GEMS, Sentinel-4.5, IRS, but also EarthCare is a very interesting mission that we want to support in this activity. Also extending to surface data. GHOST is a data set from BSC, which is very interesting collection of surface data that we will also have a look at and will be using for the work. For greenhouse gases, we will make use of COCON, which is a new network that's now available, but also focus on things like the deposition, which Johannes also mentioned, and aerosol composition. Another thing that we are working on is also to see, so we have these two evaluation servers, and we really want to integrate those two and work towards a common architecture and look again at how the two servers and take the best of both worlds, let's say, and develop sort of a more homogeneous system for that, which can also be used for the evaluation of new experiments that CAMS is performing. And then, of course, we are looking forward to the evaluation of the new reanalysis. And a last thing I want to mention here as for innovation is that we looked at headline and skill score development. And that's shown on the next slide. And that brings me to the end of my talk, because that's sort of covering a very important question. Is CAMS really improving over time? And we have seen all these efforts in the development of the model and the data simulation. So is that really paying off? And we had a headline score study in the past year where headline scores are scores which can monitor improvement over time. And this is something, so we developed a new score and we looked in more detail into an ozone score. And the results from that are shown here. So on the right, you see the ozone common area fraction score, which we are already reporting for some time, but we studied that in more detail. We looked at the stability of it, and we have improved that score. And on the right, you see a new score where we looked at the AOD, comparing with AeroNet, and especially looking at the high and the more extreme AOD values and how well these are captured in CAMS. And the nice thing is if you sort of make fits through these time series, so they go 10 years back in time from 2015. And we see that there is really a positive slope there. And so both for AOD and for ozone, we can see a steady progression and improvement over time. Okay, so is CAMS improving over time? Yes, at least for ozone and AOD we can really say so, I think. And that's it. Okay, thank you.
Thank you, Henk, for a very clear overview and for adapting to the technical issues we have. All right, any questions for Henk? Any questions? Yeah.
So actually two questions. Dominika Laskow-Krzyżewska, UMedSat. First one is you have quite a number of data sets that you are including in the evaluation. Are you storing all of this data? Because, I mean, there is validation server for CAMS, there's for Tropomi, and there will be for S4 and S5. And, I mean, everybody is doing their own things. And I understand that everybody has maybe a little bit different needs. But yeah, first one is basically technical. Are you storing it all? And for also archiving for a long time. And then the other question is, if you want to include new data sets from the Global South, then what is something that helps you and what is something that prevents you to do that?
The first one, yeah, so indeed, I mean, it's really also very much about communication, because the model developers also do their own evaluations. And so in basically all the different contracts, they have a validation component. So it's really important to communicate and to work together. And that's also the reason why now, also led by Sander Niemeyer, we are looking at this architectural design document. And we want to make the whole thing very flexible, that you can tap in at different locations. So, for instance, you can there's an access point to the observations, access point to the evaluation results, access point to statistics, and then also it can support different visualizations on the website. And yeah, we want to homogenize this and also document much better. So how the observations that we use, recommendations on how to use them, which stations are good, which are maybe less representative, things like that. And also document better the approaches to make the comparisons. So that's why we now have this activity, and we really want to communicate that with the other parts of CAMS. And the second question was about, oh yeah, the new data sets. Yeah, often it's quite difficult to get information about new data sets. So what are the procedures? How are they quality controlled? So really, we are trying to contact the providers, also with questionnaires about this, but that's not always easy.
All right, thank you very much. I think we're ready now to go to Luca's presentation. Apologies, Luca, for the delays in this, but hopefully it all works now.
Yeah, so this also gives me the chance to redo my first slide, because earlier I forgot to say that, of course, this is work of many people, not just me at the center. Yeah, so there was a collaboration of many people, mostly from the greenhouse gas activities team. And yeah, in this presentation we'll go through what we've been working on recently. And of course, the greenhouse gas activities in CAMS, they include many products. Of course, we have the IFS-based activities, which we run at the CNWF. So we have a global analysis and a daily forecast for concentration of CO2 and methane. But then within CAMS, we also have people working on inventory-based and activity-based emission estimates. We have people from recently, there is this new methane hotspot explorer activity and product, and also there are people running global monthly GHG flux inversion. So basically, each of these activities will have a presentation later today. But I will focus on the IFS-based activities. And so there are two main products that we produce. One is an analysis. It's a near real-time analysis, meaning that it's 4 days behind real time. And it is at 25-kilometer resolution at 137 vertical levels. There are 4 analyses every day at the synoptic times. And yes, and it includes global atmospheric concentrations of CO2 and methane. It's, of course, an analysis, so it's a product of data simulation. So we use the IFS for the VAR algorithm that we use at ECNWF. And in this system, we jointly optimize the atmospheric concentrations and the meteorology. And the observations that we use are YASI and GOSAT at the moment. There are news now, I will cover this later. So yeah, we assimilate basically total column retrievals from IASI and GOSAT. And I'm also making here a comment about the fact that the climatological background error covariance matrix that we use in the data simulations come from an ensemble of data simulation. And then we have the forecast, which is produced every day, and it runs for 5 days, and it's at a high resolution. So we have a forecast of 9-kilometer resolution, again for both methane and CO2. And this is also provided to other services of the people, to, for example, to the EUMETSAT and ESA for to compute a priori estimates for satellite retrievals, and then there are other groups that use this product as boundary conditions. So I will, like Johannes did, just go through some of the news, some of the new developments that are coming up with 50R1. We don't have an implementation date yet. It will happen at some point. And I'll divide the developments into data simulation developments and model developments. So for the data simulation developments, we have the assimilation of tropomi methane, which hasn't been done so far. So we will start in 50R1 to assimilate tropomi retrievals alongside IASI and GOSAT. We have revised the background errors for CO2. I will say later why we did that. And then we have also implemented CO2 anthropogenic weekly emissions instead of monthly emissions. So, starting with the assimilation of tropomi, one of the big advantages of assimilating tropomi is that currently in our system we have, as you can see in this plot of vertical sensitivities, so currently we are assimilating IASI, which is a blue line, and GOSAT, which is the green line, and their vertical sensitivity is very different. IASI peaks around the top of the troposphere, even the bottom of the stratosphere, while GOSAT, basically it's more constant, but it peaks at the surface. The issue, though, is that if you check the actual number of observations, this is just for a month in 2024 as an example, but this would be very similar during the year, you see that in this histogram, like the number of GOSAT observations that we are actually able to assimilate every month are very small. And this means that basically we are only assimilating a lot of IASI observations, but then we have only a few GOSAT observations. So there is a big benefit here in assimilating tropomi, because tropomi gives us a lot of observations, a lot more of observations. And also it has the same or very similar vertical sensitivity to GOSAT. And so then we check whether there was a benefit from assimilating tropomi. And what we find here, so here I'm showing a TCON time series, model minus observations for the 2 cycles, 15R1 and future 50R1 cycle. What you can see here is that there was a seasonal cycle before in terms of bias, and now there is a constant positive bias, but at the same time in the summer the bias is slightly smaller. And then if we check other validation, other observation, other data sets of independent observations to do the validation of the system, we see that we actually reduce the bias at the surface for methane compared to the previous system. So here you see that the red square is basically the new cycle, the green circles are the old one. And so the bias is reduced. The only thing that we have a small degradation in the total column, which is actually reflected in the TCON observation. So overall, we think that this is beneficial to the system, and so that's why we will start to assimilate tropomi from 50R1. The other thing that we're doing is we are going to taper the CO2 standard deviation in the background covariance matrix near the surface. And this, I want to stress, it's just a temporary solution, because when we change the background error in background covariance matrix in 4901, we introduced a bias at the surface for CO2. And that was due to the fact that, if I show you now this plot, you see that in the, so these are vertical profiles of increments. So you see that near the surface in the two plots here, which is the old cycle 4901, you see you have these very strong increments near the surface. But if you remember what I showed you before about the number of observations, that was for methane, but for CO2 would be very similar. So basically, we have very little observation at the surface, and despite that, we had huge, relatively large increments near the surface. And we didn't like that because the surface wasn't really constrained by a lot. And so we are, and these increments were creating a bias at the surface, and so we had decided to temporarily taper the standard deviation near the surface. And the new cycle, so the bottom plots here, those increments are gone, and we have not made any change upper in the atmosphere. So yeah, this just to reflect that tapering the standard deviation removes those increments. And so then we run a validation to see what was the impact of this change in the system. And this is actually quite good. So we have across the scores, bias, root mean square error, and standard deviation, we have an improvement. We are, though, decreasing the correlation coefficient. Right, so then we go through the model developments. The only model developments that we will have in 5001 is that we will change the emission from monthly to weekly. Again, here we check what was the impact of doing that. And so first we check the mass, the CO2 mass, in the stratosphere and the troposphere. And you can see here that basically there is not a lot happening. There is a small positive impact, as in the sense that we are increasing the mass slightly in both the troposphere and the stratosphere. And then if you check the difference, the spatial differences, we see that there is a small positive difference at the tropics and over Asia, so there is slightly more CO2. I don't remember if this is at the surface. But in terms of score, overall, we are not really, it's not really changing a lot. So it's a neutral change, but this helps with other activities at ECNWF related to future developments with the emissions. And so we decided to include this in the new cycle as well. So as a summary, at ECNWF, we continue to provide near real-time service, including a global analysis and daily forecasts for CO2 and methane concentration. And some new developments coming in 50R1 relating to the assimilation of tropomi, the tapering of the standard deviation at the surface, and the use of CO2 anthropogenic emission, weekly CO2 anthropogenic emissions. And talking about plans, so we had some presentation yesterday. There are some new exciting missions which are coming, and we will start to assimilate them in the future, hopefully soon. GOSAT-GW is one, but then we have microcarb, Sentinel-4 and 5, which are relevant for both CO2 and methane. And so we do need to improve our coverage of observation, especially for CO2, because at the moment it's quite limited. Then we have, of course, other developments relating to the emission inversion that Johannes mentioned for NO2, but also for other species in the longer term. And so there is going to be a presentation later today by Nico Bousseret, which I just want to refer to here. And just talking about the developments related to the emissions and the fact that we are now assimilating tropomi, I just wanted to show you that there is some activities right now at ECNWF about trying to see what tropomi does in our global system. So there was some work done by a colleague of mine who tried to assimilate tropomi observation and see whether we can see plumes in the IFS assimilating tropomi plumes. And so we noticed that the pre-processing that we do of the observations have a big impact on their assimilation, and that super rubbing and the first guest departure checks play a big role in deciding what is assimilated in the Fodivar. And so this is just wanted to credit one of my colleagues who is doing useful work to make the system better and better. And I think that's, and there is also about this a presentation later today about the. So this was a activity related to the hotspot monitoring, the CO2, the methane hotspot monitoring. So there is a presentation later today, and yeah, I think that's it.
Thank you very much, Luca. It's time for one question. Everything clear? Oh, there.
I was wondering about what you said about Sentinel-4 assimilation. So Sentinel-4 will not provide methane nor CO2 because it does not measure in the sphere range. But I was wondering then if for you're planning to assimilation of, for instance, NO2 would help with CO2. So do you have basically NO2 and CO2 emissions somewhat coupled?
Well, regarding Sentinel-4, isn't it methane included? But anyway, no? Okay. Anyway, so there are some activities within Corso, which is looking into use co-emitting species. So that is happening at some point, not soon, but yeah, we're doing work in the context of the emission inversion system to link the two. So yeah, there is some work done at TCWF about co-emitted species. Yeah.
Yeah, no, that's right. I mean, it was in Auke's presentation yesterday a little bit, but that's work in progress to see how we can use NO2 observations to constrain CO2 emissions.
In the next develop cycle. Sorry,
No, it's not in the operational cycle.
Yeah. Okay.
No. All right.
Okay, so let's start slowly with our next session. So before the lunch break, we will deal with two topics, so the regional activity, regional services, and what also relates to emissions and fluxes. So let's start maybe now, because we'll be short in time, with the regional activity. And I would like to, welcome Cécile Cazalet, who coordinates the CAMS 40 regional air quality products. So Cécile, floor is yours.
Thank you, Laurence. Good morning, everybody. So I will present you some slides on CAMS 240 bis, which is a regional air quality product service. I am the new service coordinator. I'm Cécile Cazalet, and I'm taking over from Gaëlle Collin, that I really thank warmly for all the work she achieved before. So, as you may know, the previous contract came to an end in April of this year, and we launched a new contract in July with the same co-management team between Ineris and Météo France. Of course, we maintain our activities during the gap between the two contracts, and as I already said, our management team is composed from people from Ineris and from Météo France. We also have experts on board on a specific task from Met Norway and FMI. So we are really happy to continue this work with our 11 partners that represent 11 models. So I will give you the name. You have DEM for Denmark, Monarch for Spain, Mini for Italy, SILAM for Finland, EURAD for Germany, JMAQ for Poland, Lotus Euros for Netherlands, UMETS for Norway, Match for Sweden, and Mocage and Chimère for France. So what is CAMS 240 bis? It's a service which includes 11 individual models and a central production unit. We have an inertia production, which is hosted in Météo France, and also a reanalysis production which is based in NRS. As I said, we produce data in near real time for 11 daily individual forecasts up to 96 hours and analysis. We also produce in near real time a median ensemble and model output statistics, which are optimized forecasts at observation sites. We produce also reanalysis data on an annual basis with interim and validated reanalysis for individual models and the median ensemble. All this production, you guess, is very challenging because we need to produce them for each model, and I thank our partner for the commitment. All this data are available on the Atmosphere Data Store, and of course, we have a strong collaboration with other CAMS services, so you can see some of them on the screen, and of course with ACMWF. So you can see on this slide the link with other CAMS services, but you can also see how we will organize our contract. You can also better understand our organization in different working packages. So first one is on observation data. The second one is on production in near real time of analysis and forecast. The third one is about the preparation of upgrades, and I will come back later on these upgrades. The working package 4, it's about reanalysis. The 5 is about user support and document, and I thank really the Copus team for the work we are performing together. And work package 6, the most important, which deals with development and which is really a major one. On surface data observation, we take it from the European Environment Agency, and they are used for analysis, reanalysis, and evaluation through CAMS 83. We also run model output statistics based on this data. In this new contract, we will work to better take into account the representativeness of station and provide a new, more complete ensemble. So as I told already, we will have some upgrades to implement. Each year, during the fall, we are planning a new major upgrade. For example, in 2026, we will add the hazel pollen species. We also plan to have each spring an optional upgrade that individual models could implement if they want. Here you can see the new timeline for validated and interim reanalysis. So interim reanalysis are delivered in February of the following year, and validated reanalysis are delivered in March of the year after. So what's new? In this new contract, we will put a lot of effort on developments. These developments will contribute to the operational part during the contract, which is really new for us. So this major work package includes the initialization of the forecast with analysis. It's a technical first steps to reach standards of global models, and that will be further enhanced afterward with more data. We have also new outputs with deposition fluxes, and as I already mentioned, we will add some new pollen species. And finally, an harmonization of our model practices. In this new contract, we will also work with deep learning method at the CRPU level, on the ensemble to spatialize the forecasts, and on the optimization of the model output statistics. In that way, we aim to enhance air quality forecast with artificial intelligence. We will also work for the future, for Copernicus 3, to improve the horizontal resolution, and also with the assimilation of Sentinel-4 observations. So we spoke yesterday about this Earth observations, and let's see what the data will be. Now we are very eager to see the result of our work, and I thank our partners, and thank you for your attention.
Thank you very much, Cécile. And there is some time for questions or comments, please. No? Leonore, yes, please.
Thank you for a very good presentation. I have a question. I'm very curious about the new deep learning system that you have. What is the basis that you are going to have? Is it going to be based on an analysis of the data from the models, or is it going to be based only on the observation and then the deep learning? I want to know how far do you go into this deep learning approach?
The best person to answer will be my scientific coordinator, so Augustin Colette.
Thank you for the question. So like you said, Cécile, we have two pillars. One of them is on the mapping and the other one is on the point forecast. For the mapping, deep learning, we are actually training on the analysis. So that answers part of your question. The other one remains at the station. And the reason why we're doing that is at the moment we have really, the reanalysis are at 10-kilometer resolution. So we have this spatial representativeness issue. And as you know very well, Leonore, we have a problem of exceedances and point forecast. So it's very important to keep this forecast at the point station. And we know from experience, and also thanks to the Atmosphere User Forum, all the work in the NCP, actually the most products are very popular. They are being used in the countries because the countries have this problem of exceedances. So basically the way we work at the moment, we still have these two ways. One is more on the mapping, like a convoluting neural network, and the other one is on the time. We're focusing on the time at point stations with recurring neural networks. We're very well aware that we have to merge that in the future, but that will be when we have high-resolution data sets. That's also why we have this other activity when we have the downscaling going to 3 to 5 kilometer resolution of the regional models. And then by that time, we will have enough training data to do both, have high resolution, so having also the ML approach in both time and space.
Thank you. Other questions? No, I don't see any. So many thanks again, Cécile. And please, Augustin, keep the floor for the next presentation about the CAMS policy tools. Over to you.
Thank you. So yes, I will have a few minutes to present you the highlight of the policy service, which started a new phase actually in January 2025. So the general scope of the service doesn't change much. We aim to provide the link between all the expertise, the scientific expertise that is in CAMS with, in general, air quality practitioner in Europe. Can it be at the European level, national or local level? So we feel like our responsibility is to ensure that we have a continued development agenda for the quality of the product and also their relevance in policy support activities. The main point of our work is really centralized on our website. So you have the QR code, the URL. And what you would find on this website is basically 4 pillars of activities. First of which is the interactive tools when you can assess and understand the air pollution episode. And then we have a whole series of work on reporting and produce assessment report, both on the short term and also on an annual basis. The activities you will find in the bottom have more to do with animating a community of users to make sure we are aware of the needs and the evolving needs of these users, so again, at various geographical levels. And what I put in the lower right is FAIR-MODE is a very important network, in particular in the application of the Ambient Air Quality Directive. It was mentioned a couple of days already, but the new directive that was revised in 2024 is referring to Copernicus Atmosphere Monitoring Service specifically. And it's very important to us to follow that closely and make sure the policy service is relevant in that context. So I will start with introducing very briefly the interactive tools. I've been showing this type of plot several times to this forum, but just to remind everyone that we're producing both episode analysis, so the everyday forecast for the next few hours and days, and the annual statistics. And for that type of product, you can look at individual cities, various type of pollutants, to try to understand if the air pollution situation is more due to transboundary events, to natural events, or also if you may want to actually infer which activity sectors are responsible for the buildup of air pollution. So that's work that started a long time ago. I must say that now we're putting a lot of emphasis in making sure the users are actually understanding well and making use of this product. So we put a lot of effort into the design, the training, documentation. Transparency is also key to have a good uptake of the service. There is a work which is a bit behind the scene in designing API actually to query this data, so it's already available. At the moment, you can access, retrieve the policy tools at cities using an API, but it's paving the way towards having a much wider extraction procedure also for not only having these 80 cities that you have on the website, but much more locations. I want to take just a couple of slides to say what's happening a bit in the engine of these policy tools. Specifically focusing on the recent development undertaken in IMEP and the Lotus model. So for IMEP, there's a lot of work that has been done in implementing what they call the local fractions in the model. For a long time, IMEP has been doing this type of sensitivity analysis, sometimes referred to as brute force, when you look what happens if you reduce the emission of the model. Actually, it's the same approach that has been used literally for several decades in the LERTAC convention. What they implemented for a few years now is actually to track incremental emission changes in the model itself, basically just by storing the Jacobian matrix of the model. So it's the same as a brute force, same as the sensitivity, but it's really incremental and online, really occurring inside the model. It leads basically the same results, what you can see on the figure and the related paper from Willem van Kaspel and Peter Wind. But just it gives the same result at 1/10 of the cost. So it's really, really much more efficient. And it's opening really new possibilities for the service, specifically the increase of the resolution. It's been operational, it's running in a parallel suite, but it will actually go live for the user at the end of the year just because we're producing this annual statistics, so we want to remain consistent. Another part of the work which is occurring in the Lotus Euros model is ozone tagging. So we have this sensitivity, brute force, but we're also tagging species in the model. Two very different approach. Lotus has been producing tagging diagnostics for particulate matter for many years, and now they introduced this technique, which is doing the same for ozone, building on the work that was developed at RIFS in Germany for a few years ago. So this way, we can actually tag various sources, both either from VOC or NOx, but for much more sectors and geographical origins as what you can do with sensitivity experiments. The main plan is to introduce that in the policy service to assess geographical contribution to the ozone episode. But we are also aware that the results will be different compared to what you have in the sensitivity experiment. So we are progressing gradually and also making sure the users are not confused, because we are aware there is always a risk of questioning between the discrepancy of the various products. I want to move to a different area of work, which is the support of the implementation of the Ambient Air Quality Directive. We mentioned briefly the fact that in this directive, there is the possibility for member states to discount natural contribution when they have particulate matter episode. And of course, dust is a very strong contributor to particulate matter pollution in the southern part of Europe, but not only in the southern part. So we are designing a new tool which will have these two bullet point feature, basically. The first of which is just to look at the maps and look at the time series, have a kind of a qualitative understanding of the contribution of the dust. Second bullet point is much more complicated, more demanding, actually a higher level of ambition, and also higher level of pressure on the service. We have to be quantitative, and quantitative in a regulatory process. So I let you think what it can mean in terms of expectations of what we do in the service. So what we design at the moment is actually to use the CAMS model results to detect the dust event and to use the observation collected in the field to do the quantification. So you're actually flagging the days and the location when you have the dust plume, but you're using the observation in situ to assess how much dust were contributing to the peak during that episode. So this way, we are designing a product which is really mature and robust. It's aligned with the guidelines that are established under for the Commission, which are actually being revised as we speak. That methodology has already been tested by a few of the member states, and we undertook a benchmark actually in collaboration with Fairmode over the past couple of years. We're really proud to say that all this benefits from the evaluation and quality control. We will talk about regional evaluation and quality control in a few minutes from now. And it's very important, it's crucial in that context to be robust on this. So this is what we do for dust, and we have a similar activity for wildfires. Again, wildfires can be part of this natural fraction that you can discount in the case of episode. Similar approach, it can be qualitative by looking at the individual episodes, but we're also looking at a more quantitative analysis to look at exactly the number of days in different countries where you had exceedances due to fires, crossing that also with vegetation maps to make sure that those fires are related to the country which is doing the reporting. I want to move to a different topic, which is the annual assessment report. We actually presented an annual assessment report several times, actually 10 times to this forum, and we saw that to celebrate the 10th anniversary, it was really relevant to work on an upgraded version of the report. So in the past, what we are showing was very much looking like a Copernicus deliverable document. Now we are moving to a totally different world with a brand new layout, an executive summary, an interactive PDF, something more easy to go through for the users. So we are really trying to promote that. We have our network of policy users. We know that the statistics and the number of downloads and readability were very good in the summer, and we're looking forward also to disseminate that beyond to the wider public. Few words on typical type of information you will find in this report. Overall analysis of the statistics. Say, okay, what was the year 24 in terms of overall trend of air pollution in Europe? We confirm that we have improvement in general for NO2, for particulate matter, so that's for the good news part of things. We're actually also trying to understand if these trends are more driven by emission changes or meteorological factor. So we are using this type of heating degree to try to deconvolute the parts of improvement in the emission factor for the residential sector, or if it's just by luck, or you can call it luck if you want, that we had relatively mild winter recently, so we have less emissions of residential heating. And on the left-hand side, on the bad news kind of things, is the fact that ozone is really flat. Of course, for the climate, you know that there are more and more extremes, more and more intense summers, but for ozone, we don't have an increase of the trend, but we were expecting to have a decrease of the peaks given the efforts in the precursor of ozone, and it's not occurring. So every year we report on this relatively flat trend. So this is the part of the report which is really focusing on indicators and statistics, and then we are looking at episodes, selected episodes to guide the policy users in the use of CAMS products to understand this episode. And I don't have time to go through all of them, but basically we have a diversity of typology looking at natural sources. So we have one case for dust, another case for wildfires. And we're also looking at anthropogenic air pollution. And for ozone, typically, we always have this message that in this example, the next few days for Amsterdam, yes, you do have a large natural contribution to the ozone burden. It's there. It's natural background. But the peak, really, what drives the peak, the reason why you have this intense air pollution episode is due to the European anthropogenic emissions, and we see that very clearly in the source apportionment tools. And again, the last one is about transboundary effect with an example of a PM2.5 episode. Just to finish, a new product that we are experimenting with at the moment is the quarterly report. So we started in the beginning of this year. So we already produced two reports for the year 2025 for first and second quarter. And it's a bit the same. So we also have this like seasonal analysis of the statistics and the episodes. And this is, I hope, very attractive also for the users. And we typically also discuss that at the Atmosphere User Forum, that there are some countries doing the analysis as we speak of what happened during the summer. I mean, typically for Spain, Portugal, and the south of France, they were very intense prevent wildfire activity. So now it's very timely to know that the policy service is working in September, October in the analysis of the summer 2025, and we publish that very, very quickly. With that, I'm finished. Thank you.
Thank you very much, Augustin, for this nice presentation. Questions or comments? Yes, please, Guy.
Thank you very much. I think this is what you showed is very important for policymakers to get all this information. But my question is, should CAMS in the future maybe try to go a little beyond that, a little further? And I'm thinking in particular about stakeholders, like, for example, the mayor of a city or the governor of a province, who wants to address the air pollution problem and try to implement a number of actions. Now, this information for people like that is still very scientific, technical, and complicated. And in fact, should we try really to help converting this in actions to address air quality? I mean, this is going beyond what you were talking about, but I can see that a lot of the people who are in charge find that interesting, but they don't know how to use this information and how to take action to respond to a challenge that they have.
Yeah, thank you for the question. Everything I presented here was really related to the assessment of the situation, try to understand what we have now. Very good question. What should be done in the future? So we move to the plans, the strategy, the projections, and so on. And part of it is in the Ambient Air Quality Directive 2024, and we're actually indeed reviewing what we can do. A typical example is national or even local authorities. Sometimes they're running this type of model to look into the future, but they don't know what the background is. CAMS has this background, and we can make it available to them. But we can also provide the information for them to benchmark and to see where they lie. I mean, if they're going beyond expectations or if just the average in Europe. I mean, you can do all kinds of things. So it's typically the type of discussion we are having also with the Clean Air Unit, to see beyond the assessment what we can do for the projection. And the comment I was making earlier this morning about the NEC is also very relevant in that context, because at national scale, what's important is the emission ceiling and the projection. And I think this is an important contribution from Copernicus. But actually, I don't have time to present all the results. There is already some tools that are doing it on the website, and you can play with scenarios. And I can say that it was one of the first tools that we operated in the website, but it was a bit complicated for policy users to actually uptake. And now we are communicating more on the source apportionment. But it's really a matter of perception. And I think it's very important also for CAMS to have some counterpart in the national level that can go to the decision-making level. So that's also the link I want to make with the policy user workshop, the atmosphere user forum, and so on, that we need some community beyond what we do to actually do the last mile of convincing the local stakeholder to use this data.
Yes, if I may maybe to complete, in fact, also this is, your question is also exactly the reason why we have these national collaboration programs that we implement with almost all the EU member states and countries, Copernicus countries. And this is exactly what we've discussed. It's true 2 days ago during the Atmosphere User Forum. And considering the programs, the projects that are put in place by the national experts, we see that there is more and more interest to uptake the policy tools and to adapt them to the national needs and to facilitate also. I think that the national authorities are also interested in using those tools, interpreting the results to get in touch with the local and regional authorities, because they very often have this mandate to be the interface between the European framework and the local needs. And I think that this is exactly the spirit of those national cooperation programs that we implement. I'm very happy to see that there are more and more use of policy tools in the projects that we have, Christina. I think that we can see that. Yeah. Other comments? Very quick. No? Stéphane, very quick.
Yeah, very interesting work, and we'll discuss offline. But I think there is great potential in, once validated, to add some of the satellite-derived information when there are dust and fire episodes, just to contrast what you have and to complement the picture, both qualitatively, because we've done that already, and perhaps even quantitatively.
Yeah, good. Thank you.
Sure. Many thanks, Augusta. Many thanks for a nice presentation. And I would like to give the floor to Michael Goss from Met Norway to discuss about the EQC activities under the regional services. Please, Mike.
So we are evaluating the products that Cécile Cazalet presented 20 minutes ago. So that's the daily analysis and forecast products and the annual reanalysis products. So that's the validated and the interim reanalysis. And of course, I have a strong team of dedicated scientists and technicians behind me. Also, I would like to thank the measurement providers. We get measurements from different programs, institutes. Without these measurements, we would not be able to do much. And this year especially, I would like to mention EAN, the European Allergy Network, who will be providing pollen measurements. So our products, that's the web server. It's daily updated. And that's probably one of the most important things I'm saying today. Please, if you're interested in model performance of all the regional models being used in CAMS, please have a look at this website. It's the first link below. I should have added a QR code. There you will find thousands of plots updated every day and find answers to many questions you might have about model evaluation. Then we have the quarterly EQC reports for the NRT products. That's the daily forecast and analysis. And then we have annual EQC reports written by or produced by INRIS with help from KNMI and CRNS about the interim and validated reanalysis. And last but not least, the annual EQC reports for the pollen evaluation. You find all these reports in the second link below on this, shown on this slide. Other CAMS regional EQC activities that you don't see, but which I find important, is a so-called alert service we have. If some of the models deliver completely unreasonable results, we will see it and we will contact the model teams. This does not happen very often. It's once or twice a year, but it's important to detect these issues quickly so that they can be resolved within a few hours or so. And then we have something which is new, the meetings with model teams. Last year, Guy Brasseur asked the question how these results migrate into model development, how they can be made useful. And now it ended up in the ITT for this service, and we will have meetings with model teams to discuss the results, support them in their development, and hopefully things will improve. So if there are any CAMS 240 model teams in the room, you will get a doodle invite this autumn already. Okay, so in order to make this presentation even more exciting, I chose a few plots, evaluation plots, randomly. So this presentation was made last weekend, and I selected the so-called last week experiment. And what you see here is ozone observed, that's the thick line, and all the models. And that just illustrates a typical issue we've had for a long time. It's the overestimation of nighttime ozone. But by and large, and I'm talking as a modeler here, we are doing well. We are reproducing the diurnal profile very well. Now, my favorite plot for today is the very recent, just from the computer, evaluation of this season, the summer season that ended just last Sunday. And if you find this plot chaotic, welcome to my world. It's what I'm looking at every day. The observation again in as a thick line, this is PM10, and episodes have been mentioned already in June. Some models overestimate, some models underestimate. We also had some episodes in August. What I would like to point out here is, unfortunately on this plot, the ensemble is not labeled. It's the light blue line, pretty much following the observations. So the ensemble is quite strong in reproducing the PM episodes. Not quite though. I will make a comment on that in a minute. So this, well, first rule is never to show large tables in a presentation, but the point I wanted to make here, on the server you will find so-called heat maps that show you for all the different regulated pollutants and for all the models the statistical parameters. For a period you can select yourself. In this case I selected 2024 and normalized mean bias as a parameter. And the upper table is for the forecasts, the lower table for the analysis, which naturally performs better. Maybe one thing to point out, sometimes you have to interpret these numbers with some care. For example, for SO2 and CO you see dramatic underestimations, but you have to keep in mind that we are at very low concentrations in Europe. We are well below the air quality standard, and in many cases we are below the detection limit for measurements. So measurement uncertainty is often 100% uncertain. So in a way we could even stop evaluating these two species. On the other hand, they are still regulated, so yeah, we will continue showing these numbers, but be careful in interpreting these numbers. One more thing, I show this plot every year. I think it's the performance plot. To the left ozone, to the right PM10, and this is from the ERA, interim reanalysis for 2024. On the vertical scale, you see the fraction of observed exceedances that are actually reproduced by the model. And on the horizontal axis, that's the fraction of modeled exceedances that are also observed. And yeah, to our taste, or to my taste anyway, the dots are a little bit too far to the left and the bottom. They should be higher up to the right. But also here, one thing to keep in mind, we had very few exceedances in 2024, less than in 2022, for example, where this plot looked better. But the fact remains that we still have some trouble reproducing exceedances, which many, especially policymakers, are interested in. But on the means, and that's the mean levels, they are also health relevant. The models are doing really well. Just to do justice to our above surface evaluators, a lot of work is done there as well. To the left, you see Tropomi NO2 vertical columns versus simulated, in this case the ensemble. And to the right, this is an evaluation against aircraft measurements. All these plots at the same place, it's Madrid. And yeah, it's an untypical example because usually in densely populated areas we overestimate NO2 columns. Here we underestimate it. But yeah, you can see plots like this, thousands of them in the reports if you're interested. Development since the last General Assembly. This list looks short, but please keep in mind this comes in addition to our operational tasks, which are a lot of work. And also a lot of innovations are hidden within the third item here, numerous changes in the EQC reports and on the web page. We have added new features, new plots, removed old ones, which we considered less useful. So please have a look again. And then the experiments with low-cost sensors. This is in an experimental stage. I wanted to show you one plot. This is very recent. It's in collaboration with NIDU. They kindly provide us with those low-cost observations for free to do these experiments. And those of you who don't like low-cost sensors, don't worry, it's still in experimental mode. Nobody sees it. We are looking at the results, and basically we see the same features, but you see here in parentheses the performances are a little bit different. And if you wonder how the quality control of those low-cost sensor observations is made, please don't ask me, but have a look at Hassani et al. They explain it in detail how this is done. I can say that out of the 15,000 stations which were available for these plots, only 2,000 selected, so the quality control is quite strict here. One important point to make is that low-cost sensors have a tendency of being clustered in cities, so we have a little bit less coverage in rural areas. Yes, this was a philosophical statement. Even if you had a perfect model and a perfect measurement, the two would in general disagree. I guess this is well known to most of you. If not, please come and see me and I will explain it to you. Some of it has to do with representativity issues, of course. Point measurements are different from area average model results, but also there are different definitions being used by modelers and observation colleagues, and we are looking into that. I said that already last year. It's a long-term development, and it's being followed up. So final remarks and future plans. To put it positive, routine evaluation and reporting without major delays. So that's the success of the contract. And then the CAMS regional models do fulfill most of the model quality at actually nearly all of the MQOs as defined by fair mode. That's the success of the models and the assimilation. I talked a lot about fair mode last year. I didn't this year, but again, go to the website, look at all the fair mode plots you might be interested in. Challenges remain. It wouldn't be me if I wouldn't point to the challenges as well, so exceedances again. But in this respect, the MOS product, the air quality forecast optimized at observation sites, they perform rather well. And then near future plan, again, we will outreach more proactively to the model teams. Medium term, I have to mention fair mode anyway. There is a very recent publication of Alexander de May, which came in July. Have a look. I'm considering including these plots in this service. Respond to user requests and resolve the inconsistencies I just mentioned. Thank you very much.
Thank you very much, Michael, for this nice presentation and philosophical takeaway messages. Good. Are there any questions for Michael, please? So, yes, Johannes, and three questions. So, yes, I've seen Johannes first, and then you and Richard. Yes.
Yeah, it's a combination of a question and a comment. We do air quality forecasting to predict air quality events, so high concentrations at a very long lead time, but very often the measures we use to represent the model performance are kind of mean values, which maybe don't reflect this so well. And I was wondering whether you also worked on the development of metrics that actually would measure this in a better way, the predictive power of events with a very long lead time.
The performance plots, they cover this to some extent. But as you heard from the CAMS 282 presentation, now I don't remember the name of this new indicator that focuses on SIPs. Yeah. So we consider that. There has been discussions about that during coffee breaks and lunch breaks already. So that might be an option. It was not in the contract, but as you rightfully say, it's important as many people are interested in especially exceedances. So yeah, I won't promise it for next year, but it's on our list of things to be considered.
Thank you. Yes, please.
Yeah, thanks for the wonderful talk. I was just hoping to get some upgrades to the way models are traditionally evaluated. So what I used to do is download the ozone observation data from individual stations and then evaluate the observation against the modeled ozone field at that grid point. So what could have been done much easier would be to create a observation, a gridded data set of observation that is also done by TOR, for example. So are there any efforts in order to use such data sets? This is the first question. The second question is, are there any diagnostic tools that you're developing so that you can evaluate several metrics easily?
Maybe the diagnostic tools first. That's kind of fair mode question, because in fair mode we have kinds of plots. I presented them last year, the target plots and the summary reports that do exactly that. They combine several metrics in one plot. I don't know if this answers your question, but that is what we are currently doing. And there are no plans of further combination, except for the radar plots that I didn't get into detail, but the radar plots recently published by Alexander de May, they show you lots of different metrics. For example, the gradients between weekdays and weekends, between summer and winter, between day and night, rural, urban. All of these metrics in one plot, which gives you a very quick overview of model performance. The other question about gridded observational data sets, maybe I'm making a fool of myself now, but I think we are doing that under the hood. We make a co-location of observations with model data, and we store that in PyAerocom, the model evaluation software we are using, but it's not visible to users. It's only visible to our. And I don't think we are even allowed to make that public, but you think we are? Yeah.
Thank you.
Yes, just a comment on your philosophical statement. We actually developed an explainer video quite a few years ago already, because we got this question from users looking at forecasts and saying, well, the measurements I get from the Environment Agency are completely different. So what's going on? So we tried to explain at least part of that statement already. So it's available on the CAMS website actually, but it's a bit hidden. But just for information.
Yeah, I haven't seen it. I will participate in the next video.
Yes, please.
Pleasure.
Thank you. Thank you very much, Michael. Thank you. Let's move on to the next presentation. So now we have the emission and fluxes session. So the first presentation will be given by Jeroen Koenen from TNO, and it's about the global and regional emission inventories. Please, Jeroen.
Thank you very much, Laurence, and for the opportunity to present to you here the work that we're doing on the global and regional emissions. And we heard a lot this morning and over the past few days about models which are predicting air quality, forecast, reanalysis, all these things. But we also heard several times regarding the importance of the emissions that you put in as being one of the most important, or maybe the most important parameter for getting proper model output. So I will give you an overview of the work that we're doing in the CAMS 261 project. So yet another number of CAMS, but this is the one that relates to the emission inventories. Again, like for everybody else that was speaking this morning, it's not just me, there's a whole team behind it, and there's so many people working on it, it hardly fits on one slide. But so it's a truly team effort. So the main things we produce, so this slide summarizes basically the key data sets that we produce. So we have regional emissions that we produce for anthropogenic sources. We have global emissions, both for anthropogenic sources, but also for natural sources that are being used by the CAMS global and also regional modelers. And then on top of that, we have a separate dedicated task to look at shipping emissions, because this is, of course, part of anthropogenic, but it has a very different dimension and a very different approach how to work on that. So our core business as emission project within CAMS is to produce emission data sets. It might sound obvious, but this is what we do. And this on the slide here, you see all the different data sets that we are producing. typically on an annual basis. So we have anthropogenic emissions, like I mentioned in the previous slide, at regional scale and at global scale. We have natural emissions, and then they are split out by different natural elements, basically. So biogenic VOCs, we look at soil NOx, we look at volcanic emissions and ocean emissions. Shipping emissions, and besides from just the emissions, because these are typically either annual or monthly total emissions, and of course, to put them in the models, you often need more details with regard to the timing of these emissions. So what we also produce for the anthropogenic emissions is to produce temporal profiles to actually break them down from annual or monthly into hourly and daily emissions. And besides all these products that we do, I will show all of them in a minute, very quickly, is that we also provide documentation to our products, of course. It may sound obvious, but it's very important if we want the products to be taken up that we carefully document what they are, how they are built up. We look at the impact of specific events, and the COVID pandemic, it seems ages ago already, but it's only a few years, was such an event, for instance, where there were quite dramatic emission changes suddenly, so we had actually the opportunity to really look at that. What's the impact that has on emissions? We provide speciation information for several of the more lumped pollutants that we have, like PM. It's really important if you put that in your model, what does it actually consist of? VOCs, same story. And very importantly, we also connect to the users within CAMS and also beyond CAMS. So within CAMS, we regularly iterate with the global and regional services to make sure that our products are basically aligned with the needs of these services. On the shipping in particular, and that's one of the reasons why it's a standalone thing also, is that the CAMS community also supports EMSA there. So that's the European Maritime and Safety Association, providing them with information on shipping emissions. So that's a little bit a different line, not through the CAMS modelers, but directly supporting EMSA there. And then, of course, like most of the CAMS services, we also work on improvement of our products and new developments, and I will show some things later on. So, regional anthropogenic emissions. So this is something that's used a lot by the regional services. So if the CAMS REC ANT data sets, we are at version 8 at the moment, which covers 20 years of emissions at the moment. These are annual data at a resolution of around 5-6 kilometers over Europe. You can see the domain and the plot on the right-hand side. The species are the main air pollutants, but also key greenhouse gases. The methodology, basically, it's based on reported data, so that's very important to emphasize here. We use the official data from the member states and the countries that are in the convention, which they are reporting to the EU and EMAP, and built on that. So what we provide in terms of emissions is consistent with what the countries report for themselves. The plots show you a little bit the trends that we have in the latest data sets. So you see here NOx and SOx projected on the screen on the left. You see that NOx, especially in EU countries, and SOx as well, they go down a lot over the last 20 years. And this is really the result, of course, of policy. This is to emphasize again, policy works. You see, if you look at the non-EU countries, which are part of the domain, it is going down slightly, but really quite not as fast. And this is, of course, the fact that the policies there are different. They are not EU. And then also there are shipping emissions, and you see there also it's going down slightly, but not much. So this is really to emphasize also the increasing importance of shipping, actually, for emissions in Europe. Only for sulfur, I want to highlight that there is you see a strong decrease from 2019 to 2020, and that is basically reflecting the introduction of the global sulfur cap to reduce sulfur emissions. Similar graph for PM and the different species that are in there, but I will just move on in the interest of time. Global anthropogenic emissions, so we have the CAMS GLOB ANT datasets, which were also shown before by Johannes in the morning. These data sets are typically based on EDGAR as a basis, combined with all kind of other data sets. And this graph is also similar to what Johannes showed in the morning, where we compare different emission data sets, either global or for specific regions, to see how they are comparing, and based on that, basically decide on the way forward. This is done at a resolution of 0.1 by 0.1 degree for the whole globe, for also quite a long time series from 2000 onwards. There was a paper describing this in detail, but I will come back to the documentation a bit later on. And these, both the regional and the global anthropogenic emissions, also incorporate the results from the shipping emissions that we will show in a minute. Then natural emissions, we have, as I said, different products there. So we have biogenic VOC emissions that were shown already before also. So again, we have a long time series for different set of VOCs, 25 in number, basically building on the results from the Megan model combined with the ERA 5 information on the temperature in particular. And you see in the plot here basically their evolution over time from 2000 to the latest year. And already last year we said like it's peaking, it's higher than ever. In 23, now 24 was even higher. And this has of course a lot to do with the increasing temperature. On the right hand side you see an example of the soil NOx emissions that we are also producing on a monthly basis at a bit of a coarser resolution. This all has to do with the availability of the input data that we can get for different components of soil NOx as well. Then we have ocean emission and volcanic emissions, which are also different products we make in the natural emissions. So for oceanic emissions, we have global emissions of different species from the oceans. It's based on a combination of different data sets. What's new there is that we are using an Earth system model from Met Norway also to actually complement the approach and improve the results that we're getting. And we have volcanic emissions building on basically the information we have from local observations. There is a NOVAC data network which is specific to observations in that area, so for volcanoes. Combine that also with ERA data, and also there we are looking to at the topomy results, for instance, to validate that and to compare against. Few words about shipping emissions. So we have there a global set of shipping emissions. This is based on IES data. So every ship has a tracker, so you know where it is. And if you then know the characteristics of the ship, you can actually build up a model that estimates the emissions for all of these things. And this has been done for quite a few years by FMI and covers both inland and sea shipping across the globe. A new thing there is that we also take into account the ambient effects like wind, waves, and currents, ice cover on the emissions, because these things, as you can imagine, will have an effect on the fuel consumption and the emissions that are being done. And here on the plot you see again the impact of this sulfur cap that I mentioned before for different sea regions in Europe in this case. Then, as I mentioned, most of the data sets are either producing annual or monthly data, and it's really important for models to be able to correctly put those emissions into the model and the forecasting to actually know what's happening at daily or hourly scale. So, therefore, we have developed in the last couple of years a data set called CAMS Tempo, and this basically gives you the breakdown factors for per source, per region, for different regions in the world. So there are data sets at the global scale, at the regional scale. They are really tailored to actually the needs of the global and regional modelers. So they can be directly used in combination with these emission inventories. And we are working actually on improving them. And one thing that we did is to look at specific countries, specific cities, because before we treated them all the same, now we need to look at them in more detail. So a few words about developments and related projects that were mentioned also yesterday. So we are working on trying to integrate results from all of different projects that were mentioned. So I want to just touch on a few. There's probably no time to explain in detail, unfortunately. But something we did in the Rye Urbans project, which is another Horizon project that wasn't mentioned, but it's also one looking at air quality, is we noted that actually in cities we have underestimated emissions from road transport. So when seeing that there, we worked on improvements, and we see that now we are doing much better. So we moved from the green to the red bars, whereas the blue bars represent the cities, and have now implemented that in the latest version of CAMS. We're also looking at comparison with satellite-based data, comparing CAMS to satellite-based emissions, and see what we can learn from that, especially for NOx. It's the best developed one, of course, there. We also have challenges. We're looking at uncertainties of emission products, which is a major area of development. It was already presented yesterday as part of the Cameo project. Hopefully we can continue that later on. We need to continue to work on the satellite comparison. I think very important. It's a new source of information, but it's challenging to really understand the differences, each one of them. Something I didn't mention, but Johannes already pointed out in the morning, is that we are working on the mosaic approach on the global scale, so putting different regional inventories in the global one to actually improve the performance, and I'm really happy to see that it does. So we'll hope to continue that in the future. Finally, there is the documentation, and you have a QR code here where you can actually find it on the CAMS website. That's an overview. We have links there to all the scientific papers that you might want to read. But all the data are available for all of you in CAMS and also outside on the ADS, but also on another portal called ECAT, where all emission data sets are basically available from CAMS and also others. So have a look at that, have a look at the data, documentation, and our current project is now ending, but hopefully in the future this service will continue, and yeah, I'll leave it, I think, at that. With thank you to the whole team of CAMS 261, so not all individually, but as I said at the beginning, it's really a team effort, and we couldn't do without all these partners. Thank you.
Thank you. Thank you very much, Jeroen, for this very comprehensive and complete presentation. A lot of work is done on emissions. Yes, so a bit long to report. Maybe you could keep your questions for the lunch break to Jeroen. Many thanks again. And let's move on. You have to go here for your presentation on global greenhouse gases fluxes. Please, Frédéric Chevalier from CEA.
Thank you very much, Laurence. On behalf of the CAMS 255 BIS team, I'm happy to report here on global greenhouse gas flux estimates. We've heard a lot about greenhouse gases since the start of this General Assembly. We heard about the launch of Microcar. We heard about the preparation for the launch of the Constellation CO2M starting in 2027, and many other items. There will be more after my talk as well. So global greenhouse gases over the globe have risen a lot in importance in institutional agendas. We are addressing them in this team through global atmospheric inverse modeling. We've been doing this since 2005. Richard reminded us yesterday about the history. So we are among the old ones, at least I am. So since 2005, we've been designing these three processing chains, one for CO2, one for N2O, and one for methane. Those are big systems that deliver 2D surface fluxes of this species every 3 hours and over very long periods of time, because we are talking here about long-lived species. We start typically in the 80s for CO2 and CH4, and we start in the 90s for N2O because the surface network evolved a bit later. We are delivering 2D surface fluxes, but also the associated 3D concentrations over time. So each product over these long periods and with all this data cover hundreds, nearly nearly terabytes of data that are delivered, and after computations that last usually a few weeks on high-performance computing facilities. So 3 big systems, and in this contract of CAMS, we have wished to harmonize some of the input data, the prior land vegetation flux maps, and the atmospheric chemistry data. For the land vegetation fluxes, so there are prior fluxes, they are refined with the inversion process. We've been designing a processing chain at CEA LSCE that starts from ERA 5. We download the data every day, we format them, we run the Orchidea land surface model at 0.5 degree resolution with 3 hourly outputs. And then every few days we concatenate the output files for distribution and visualization. You see the outcome at the bottom with 2 maps, one for CO2, one for N2O. Methane will hopefully in the next months join the pack. So that's for the land vegetation fluxes. Atmospheric chemistry, this is KNMI. KNMI designed a special configuration of IFS Compo to run what I would say a golden experiment that starts in 78 until near real time, so it's run continuously. It's a golden experiment that is as homogeneous as possible, even though some of the auxiliary data, and in particular the surface emissions, could not follow the same inventory from start to the end. So there was a lot of harmonization and validation downstream. This page, this slide, only shows results for methane, but the golden simulation contains the information for the 3 species at once, plus other ones if needed. We see on the top left the evolution of the lifetime of methane starting in 78. So it decreases initially a bit and then stabilizes with large variability around the mean. And on the right, you see the loss rates of methane. So this is really the variable which is used by the inverse modeling system. You have 4 lines because it's 4 different months of the year 2019, I think. 2018. On the left, you see the loss rate in the boundary layer, and on the right, the loss rate in the above the boundary layer. So this data is being produced, and TNO, who is in charge of the inverse modeling system for methane, has already picked it up, compared with the data that they had been using previously, that was less, I would say, reliable, less robust. On the top left, you see the previous global loss rates, with a trend very clear until 2010. With the new loss rates, we don't see the trend anymore. There is a more stable trend from start to end. With all in all, I would say larger loss rates. With the new data, larger loss rates, it means that our prior simulation provides smaller atmospheric concentrations. Smaller atmospheric concentrations, when we run the inversion, we get higher emissions during the first couple of decades, therefore changing the trend of the emission over time. And this is really something that we want to have as robust as possible, because it's something which is looked at a lot to understand what's been going on for greenhouse gases. Another important development for the methane processing chain is the ongoing porting of the TM5MP transport model, which is behind the hood, under the hood in this processing chain. So the porting of this transport model on GPU. You have here on this slide different tests. I'm not giving the detail, but you have different configurations, 2 different compilers, and bars that correspond to the computing time of the 1 CPU or 1 GPU. 1 GPU, it's in red or in pink, and no surprise, the pink or red bars are much smaller than the other one. We just still have an issue to solve to address the extreme right. You see copying and copy out. It's lost time between the host and the device transferring data. This is being addressed and will hopefully soon disappear. The processing chain, the inverse modeling chain for N2O is managed by Nilu. The highlight this year is the increase of the resolution from roughly 2 degree global to 1 degree global. So with this move, we have the 3 species roughly at the same resolution. Everybody is at 1 degree now. In terms of accuracy, I would say that the new version at higher resolution doesn't change a lot the prior simulation. So you see the previous course resolution on the left in blue at different stations. The new higher resolution curve is in green, very small differences, but at some stations we have a move in the right direction compared to the observations in black. So when there is a change, it goes in the right direction in terms of phasing and in terms of amplitude. This is before the inversion, so we gladly take this asset. And in terms of flux increments after the inversion, there are changes, previous at the top right and new with the bottom right. You see less increments with the higher resolution over the Americas, stronger increments in Europe and Southeast Asia. Then the inversion system for CO2 that we manage at CEA LSCE, the highlight is another change of the grid, not in terms of resolution because we are still around 1 degree, but we are moving to square cells to hexagon cells. The advantage is the speed. We gain a factor of 2 with this reformulation of the code. In terms of accuracy, small changes that again go in the right direction. It's the plot on the left. The blue curve, the blue numbers are the standard deviation with the new version, and it's usually below the standard deviation with respect to surface measurements at different stations that are ordered by increasing latitude. And these blue numbers at a number of stations are below the orange numbers, so we are happy, even though it doesn't really change the whole picture. And also in terms of inter-hemispheric transport time, which is illustrated by the SF6 simulation on the right, we have slightly less bias in the northern hemisphere, so we gladly take this advantage. To compare the output of the inverse modeling system for CO2 with UNFCCC numbers, we need to have maps of displaced carbon. So this is, for instance, where carbon has grown in crop fields and where it has been consumed by human and animals over the globe, and in particular in urban areas. We have updated our database from version 5 to version 6 by updating the input data from FAO, IEA, and MODIS, and revising the code for the IEA processing. So I'm not giving any detail, but maybe what sticks out is Nigeria that doesn't stick out anymore over the African continent, further to an update of the FAO data. With our systems, and I'm thinking here about CO2 and CH4 because we are missing satellite data for N2O of high quality, but we have this capacity to assimilate the satellite data for CO2 and CH4. We are using it, and therefore we can provide inversion results very fast after real time, or well, I would say low latency, a few weeks, couple of months after data acquisition, and therefore we can explain rapidly, provide an explanation for the recent evolutions of the growth rates of these gases. For CH4 last year it was maybe not so exciting because the growth rate of methane was aligned in 2024 compared to 2023. But for CO2, NOAA diagnosed an exceptionally high growth rate, I mean unprecedented, never seen before. And with the OCO2 data, we could identify the tropical bands and the Amazon, tropical Africa as the origin for this anomaly. In these regions, there were unfortunately large drought periods that triggered this anomaly. This is taken up in particular by the Global Carbon Project for fast updates of their global carbon budget, so fast and concise. There was one paper last year and 2 are in the pipeline. We are using OCO2 for that. There is a question mark here because, as you may know, OCO2 may be terminated at the end of this month, unfortunately, even though it's the best instrument doing this job in space right now. So if unfortunately the satellite is terminated, hope it will not be the case, but if it's the case, then we will study the possibility to use the GOSAT data that are great, and we are really thankful to our Japanese colleagues, but arguably OCO2 is currently the best, so it would be a real loss if this healthy instrument was disconnected. I'm finishing here with just a demonstration. It's a test that we've been doing with the IFS to demonstrate a possible CO2 MVS configuration. There will be more discussion about the whole concept of CO2 MVS by Nicola a bit later. The idea in our test here is as follows. We have satellite data that inform about the concentrations of methane and carbon dioxide, and they are assimilated by the ECNWF system, the IFS4 DIVA, over a short period of time, say not longer than a day. Even though we are talking here about long-lived species. So most of the information from the satellite is transferred into an optimized initial state of carbon dioxide or of methane at the start of the short data assimilation window. This is not so interesting per se, and we'd like to convert this information into an information on the surface fluxes in the weeks that precede the data assimilation window. From a mathematical point of view, within the Bayesian framework, this can be done cleanly by normalizing with the prior error covariance matrix and feeding the output into the adjoint of a transport model. And in this test, we have been using the transport model of our inverse modeling system for our service. So it's coupling the IFS and the LMDZ transport model with the 2 interpolation interfaces. You have the map here that shows the normalized flux increments backward in time. We have reached 300 hours behind the data assimilation window of ECNWF. You still see some small patterns vanishing away progressively. So this is something that technically works, but we still need to seize it from a scientific point of view. It's food for thought. With this, I'm finishing. It's really an exciting period, even more than before, even more if it was possible, to work on greenhouse gases. Thank you very much.
Thank you very much, Frédéric, for this very good presentation. I think that we have to move on, but please keep your questions for the lunch break. Thank you very much, Frédéric. And I would like to welcome Ana Lopez from S1. And Ana, you will talk about the methane hotspot monitoring and detection activities. Please, floor is yours.
Okay, thank you very much. Hello, everybody. Yes, as she mentioned, I will be talking about the development and provision of methane hotspot emissions from satellite observations, which is a new CAMS service that started on May 2024 and includes both operational service as well as ongoing research. So first, a few words about Tropomi, which is on board of the Sentinel-5P. And it is a push-brom spectrometer that scans the entire Earth every day. And in one of those orbits, we can have around 2,600 kilometers strip, which allows us to measure 100 of observations per second. So with 14 orbits like this per day, we are able to have a daily global coverage at about 5/7 kilometers resolution, which is sharp enough to see emissions at the scale of a city. So Tropomi is measuring the atmospheric column of multiple species, but one of them is methane, which is particularly interesting because it is responsible for 1/3 of the global greenhouse gas emissions, and also it is trapping 30 times more heat than the CO2 with a shorter lifetime of about 10 years. But most importantly, the half of the methane emissions can be actually reduced or are technically feasible, and then 25% of those at no net cost, which makes it a very attractive target for greenhouse gas emission reductions. So this unique combination of coverage and resolution is allowing us for the first time to have a very global overview of highly concentrated point sources, which we can detect at, with a detection limit of about 8 tons per hour. But of course, the global coverage is limited by cloud-free observations. So here you can see in the image a single Chopomi overpass zoomed in over Turkmenistan, on which the colors are representing the methane concentrations and the arrows are representing the wind field. So here we can recognize a couple of plumes, which are those groups of, let me see if I can point it here. So those groups of pixels that are enhanced above the background, but are stretching along the wind direction. And here the black cross is also representing the estimated source location for one of the plumes, and it is upwind. So, for example, think about an oil and gas pipeline leak that could be coming from, could be emitting there. But the thing is, Chopomi is delivering a few millions of these observations per day. So we need an automated and efficient way to find our plumes within this big amount of data. So for this, in our group, we use a two-step machine learning pipeline, which was developed by Berend Scout, a fellow colleague at Esron. And in this pipeline, in this first step, we use a convolutional neural network that is trained to identify plume-like objects in the methane field. And I want to be clear here that this is trained to identify point sources and not more dispersed area sources, right? But finding methane plumes is not always straightforward, because sometimes what looks like a plume could be an artifact coming from land features, albedo, or coast features. So in this case, we use a support vector classifier that takes additional Chopomi information. And then it finds correlations, and if it finds correlations with one of more of those variables, or there is a mismatch with the wind direction, this is most likely not a real emission and therefore probably an artifact. So here is an example of one of these emissions that were classified as plume-like objects. So here on the right, you see that the albedo information has no correlation within the plume. No, yeah, on the right. And then on the other side, we see another plume, but actually we see a patch of pixels, of bright pixels, over here that are suspiciously correlated with the methane field. So therefore, this one would be classified as an artifact because it's not really coming from the methane retrieval. But then we add an additional human verification step that is very important to filter this false positive that we could have from a machine learning model, of course. And then on this step, each week, two experts label these detections from the former week, and they label independently, and then they compare the results. And then the ones that are a bit more difficult, they are brought to a bigger panel of experts, as well as the most interesting detections. And then after discussion, the most doubtful cases are set aside for further research. And the most confident plumes are actually displayed in the, provided and displayed in the Methane Hotspot Explorer, which you have seen along some of the earlier presentations, and also you can find in this QR code over here. I hope you can see it clearly. And so before I walk you through the website, I would like to take a moment to thank the CAMS website development team for all the work that they have put on this very beautiful platform. So with that said, this is a video of what you can find on the platform. And here you can see, yes, all the emissions provided to CAMS from 2024. You can either look at the full period or select a specific time range. And here each detection is representing, each point is representing one detection, and the bigger the circle, the larger the emission. Those emissions are calculated using the integrated mass enhancement method, and the colors represent the estimated source type, which are based on dominant emissions from bottom-up inventories. But to be clear, this doesn't necessarily mean that the emission is coming from there, but this gives us a nice idea of where the plume could be coming from. And then you can explore the global distribution for different source types, like coal, oil and gas, urban and landfill emissions. Or you can go into more detail, and for each of our detections, we also provide this detailed zoomed-in information, in which you can see the tropomi methane concentrations, and the white lines are representing the wind field. But you can also find the source rate, the uncertainty, the exact date of the detection. And yes, so this is the full map. And then, if we look at the data from 2024, we can see, for example, that the United States was the country with more plume detections, with about 31 detections, coming mainly from oil and gas sectors. We have on the second place Turkmenistan, with 363 detections, also mainly coming from oil and gas sectors. And then on the third place, we have China with 259 detections, but in this case, they are coming from coal production. As part of the service, we also provide a methane alert system on which we pick the most significant tropomi detections, and then we use them as an early warning to flag emission hotspots that need to be followed up. And then we check those hotspots with higher resolution satellites, such as Sentinel-3. And then we provide this information to other projects, such as IME on Mars, for further action. But we also provide interesting detections to CAMS. So, for example, we had this early this year, the detections coming from the Fentale crater in Ethiopia. And finally, we offer support to the development of the CAMS global methane monitoring system, which you also heard about a little bit earlier this morning. And here, we compare our emission quantifications with those coming from the IFS inversions. So on one side of the comparison, you have the IFS emissions optimized using tropomi data and other satellite data. And on the other side of the comparison, we have the model independent emission estimates coming from our detections. But the key point here is that those super emitter events do happen, but they are often not taken into account in the bottom-up emission inventories that are then used into the inversions. So assimilating the tropomi data is already helping a lot with this, but of course the inversions have limitations in representing these highly concentrated sources. So here, this is a big research question on which the comparison with our method comes to add a lot of value. And I think this is my presentation. Thanks a lot. And if you have any questions, please contact me.
Thank you very much, Anna, for this very nice and comprehensive presentation. Very well done. Thank you very much. And yes, please, if you have some questions for Anna, just ask during the lunch breaks. Many thanks. Last presentation for this morning, Nicolas, you're here, will be given by Nicolas Bousseres, and it's, Nicolas, you will give us an update about the CO2 MVS system that is currently under development. So please, Nicolas.
Can you hear me correctly? Yeah. So hi everybody. It's really my pleasure today to present on behalf of the whole team, the whole CAMS team, about the recent development of the CO2 MVS at ECMWF. I would like to start, so from the start I would like to stress that the CO2 MVS is a very big project, and in fact there is a large consortium of partners that have been working on developing this system. It started in 2017. So what I'm going to show here is just basically a part of this work, which is related to the development of the global component of the CO2 MVS within the FS. Okay, so CO2 MVS stands for CO2 Emission Monitoring and Verification System, but in fact, the ambition for this project extends beyond the monitoring of greenhouse gas emission. And the motivation comes from both the climate and the air quality perspective. From an air quality point of view, we know that the concentration of pollutant and ozone precursor are mainly driven, as was said before, by emissions, and not really the initial concentration, which is what we have been optimizing in CAMS for many years now. And so the problem is that we rely on those bottom-up inventories that are quite good and are improved every year, but still they don't quite capture the significant day-to-day variability which is necessary to provide reliable air quality prediction. Now on the greenhouse gas aspect of the problem, so the atmospheric monitoring of the atmospheric concentration of greenhouse gas is not the only challenge. We really need to accurately attribute the source and sink in order to design efficient climate mitigation policy. And so again, the bottom-up inventories we rely on are spatiotemporal scales that are not quite good enough so that we can understand really the complex processes at play and therefore design those policy efficiently. So the solution to those challenges are top-down inverse methods where we actually combine near real-time in situ and remote sensing measurements with models to provide timely update on the source and sink that control the observed temporal variability of both the greenhouse gases and the air quality related species. So a quick overview of the timeline with the main development leading to the CO2 MVS. So in parallel to the launch of key missions like Sentinel-5P that we mentioned before, Sentinel-4, etc., and in the future CO2M, in parallel, a lot of research and preparatory projects were launched whose goal was really to learn how to best exploit this wealth of information. And so in order actually to realize the vision that was laid out by the CO2 Task Force document to build this European capacity to monitor greenhouse gas emission. So we are now in the operational ramp-up phase for CAMS, and so we aim to provide a prototype for the air quality emission component of the system in 2026, and then later the full system, the configuration which will also account for the optimization of the greenhouse gas emission with a long window, very much similar to what is done with offline system. Quick overview of the approach. So we combine, as you know, observation, the available atmospheric observation with prior information under the form of usually bottom-up inventories. We put that in an Earth system modeling framework, and we produce a statistically optimal estimate of relevant variables. And so those outputs then are used to generate emission monitoring data, to build user support structures, policy tools that will basically address the need of different type of users at different scales. So from industry to government and policymaker to the scientific community, and from global initiatives such as the Paris Agreement to local initiatives such as policy for green cities. This slide have been, or a similar slide have been discussed by Richard yesterday. So just to say that we are living a period where we have a very exciting period where we have a lot of observations of atmospheric CO2 measurements, and also methane and other species. Nevertheless, it's very challenging to extract the relevant information, in particular the signal that correspond to the anthropogenic emission. So we rely a lot on those inverse methods. So what is the approach? So we rely on four pillars here. First, the integration. We want really to integrate our emission system to the existing IFS framework and to exploit its operational efficiency and maintain its cost efficiency. We want to exploit also co-emitted species such as NO2 and CO2 further constrain anthropogenic emissions. And we can do that because the chemistry is embedded in CAMS, as you know. We want also a multi-scale approach because this problem have basically, we need to have global estimate budget at country scale, but also at much higher resolution. So for that, we rely also on other products that are developed with a higher resolution system. And the idea here is to assimilate that into a whole multi-scale system. And finally, obviously, we need a good uncertainty quantification estimate. And for that, we rely on some operational tools that are available. So I won't go into much detail here. I will jump quickly to the results. But as you know, we optimize emission using a 4-level algorithm within the IFS. We are using a short window of 12 hours for now. And so I will present the first results we obtained by doing extensive evaluation within the Cameo project and running 2 years, 2019 and 2022. Evaluating in particular the NOx and the methane emission. So, do we improve the air quality forecast if we optimize the emission? And the answer seems to be yes. I mean, we did some preliminary experiment. Here I'm showing the mean bias in the forecast at the surface for different stations over Europe, USA and China, and for 2 species, NO2 and ozone. I'm showing the time series. The standard analysis from CAMS correspond to the red line, and the green line correspond to the new system with the inversion. And you can see that, except for China, where actually we have both improvement and degradation depending on the day, for the other area, Europe and USA, we significantly improve both the NO2 and ozone concentration. We can also look at the emission, and here I'm looking at 4 power plants. We compare the CAMS inversion results, it's a time series, monthly average time series, with the DESCO system, which is a similar top-down inversion system, but which operates at much higher resolution. So we consider it as a reference here. The CAMS prior is shown in orange dot, the posterior is shown in blue dot, and the blue line is the DESCO estimate, and you can see that we capture much better the temporal variability when we optimize the emission. For methane, we got also interesting results. So I'm showing here the comparison between the global methane budget in blue on the histogram here, and the prior IFS in green, and the posterior in orange. And you can see that either we don't really change emission, or when we do so, we actually go in the right direction. We are much closer, as you can see, to the GCB estimate. It's true at the global scale, it's true also at regional scale. For the in-situ observation, here on the bottom, we are looking at time series from the OSPAC dataset. Observation in black dots, CAMS standard analysis in black, and inversion in red. And you can see also that we improve significantly over some period the match to the observation. What we did also is that we tried to use the NOx inversion product and applied an emission ratio, the NOx CO2 emission ratio, to produce indirectly this new CO2 emission product. And we found very interesting results. If you look here at the comparison with the reference, the GCB product here in blue and the CAMS posterior in dark orange, you can see that for both years, we actually significantly improve the fit to the, we are getting closer to the reference estimate. It's true also at regional scale. I won't comment too much on it. If you look at the concentration at the surface also, we are looking here at the biases between the model and the observation for urban sites, background sites. And you can see that over urban sites, we also tend to improve the fit to the surface concentration. If you look at the orange dot here, the posterior, it gets closer to the y-axis. So we are doing a good job also here. I will move directly, I think, given the time I have, to the last slide. So one of the main work we are doing now is moving from this short window assimilation to the long windows. As you know, and my colleague Frédéric mentioned that before, because we are dealing with species with long lifetime, we need actually to have a long window optimization system. And so we are extending the current assimilation window by, as he explained, using some offline adjoint transport, and also combining that with the IFS ensemble-based covariances via the so-called EDA. So it's a non-intrusive approach. We don't modify the four-level algorithm. We just extend it in a cheap way, if you want. We need also to improve the prior error covariance matrix. So it was done already as part of Corso, but we continue this work. And the goal, as I said, is to have a fully integrated system that deal with both the GHG emission and the air quality-related species to improve the results on both fronts. And with that, I will thank you.
Many thanks, Nicolas, for this very clear presentation. It's the end of the session, but maybe if you have 1-2 questions for our speakers of this session, so Nicolas, Anna, Frédéric, and Jeroen, please, we can take maybe 2-3 minutes to answer burning questions related to emission and flux estimates. Where? Sorry, yes, Ernest, please.
It's for Frédéric. It's about the methane loss rate. I have seen that they have updated the loss rate. What I would like to know, in the profile, which part of the profile do you improve? Stratosphere or the troposphere? Which one?
For Frédéric.
Yes.
Well, I cannot comment actually on the methane itself improvement, but what we improved in the loss rate compared to the earlier version that you had, it was really a first shot that we did. What was it, 8 years ago? And now we did it carefully. So I think in the earlier version there was issues with mass conservation, which is solved. So there was a strange drift. And now we have a stable IFS version, and I'm rather proud. It's a very nice data set, in fact. So it's first. I mean, it's maybe experimental. I think many of you will agree it's experimental, but at the same time, we looked at carbon monoxide, and it gives a very good signal, actually, which gives impression that the CO itself is also stable. We also looked at ozone total columns, so also the stratosphere is rather well constrained, which gives confidence in both tropospheric and stratospheric consistency of the loss rate. Sorry, it's a bit long response.
Thank you very much, Vincent. Thank you. Last comment, last question. No. If no, really many thanks to all the speakers this morning. We had very excellent presentation, very comprehensive in a very packed time. So many thanks for this effort. So now we'll go for lunch until 1:45, I think. So please be back really on time because we will start at 1:45 sharp. Because we don't want to finish too late this afternoon. So see you later. Thank you.
Okay, let's get started. So we've heard a lot of things about CAMS in its current phase. In this final session, we have the opportunity to hear a little bit about the outlook for the next phase of CAMS, CAMS 3, but there's also room for interactions, questions, clarifications, and Laurence and Hugo will try to answer these as best as they can. Of course, there's still quite a bit of uncertainty, but they will first explain a bit about the process and the thinking that's been going on towards defining CAMS 3. So I don't know who's starting.
So thank you for the introduction of the topic a bit. So I will take just the first bullet of this slides because it's a bit about the process leading into the next funding cycle. And so I would like to say a few words about the process in general. So the EU budget is organized in multi-annual planning periods, which are called multi-annual financial frameworks, so MFF, as you see there on the slide. And the next of these planning cycles is then going from 2028 to 2035. 2034, actually. So currently, we are in our current financial period, as you know, goes from 2021 to 2027, and this means most of all the contractual arrangements for your service are as well aligned with this period. And then you need to do the leap of faith, and you will arrive in the next financial framework. Yes, so as this is basically covering all the budget of the European Union, so not just Copernicus, not just space, not just research, it's really everything in one. So there's a quite significant preparation period, and these documents take form of really as well pieces of EU legislation, which means they follow the normal legislative process within the European Union. And that is that the European Commission, which is the executive of the European Union, makes a proposal, and then the co-legislator, which is on one hand the Council of the European Union, and on the other hand the European Parliament, they then iterate, arbitrate amongst themselves, and finally adopt a final version of these documents and this framework. So that you can easily imagine that this process takes time and iteration between member states, and as well with the different commissions of the parliament, committees of the parliament, take quite some time. So this means that the Commission has proposed on 16th of July this set of documents, and now in the coming 2 years or so, the public, the stakeholders, the parliament, the member states all will work on that, and finally hopefully brings us to a decision in the second half of 2027. And from our side, in order to make, I would say, an informed proposal for the content of the work, to make as well an informed estimation of the funding needs for Copernicus, we have asked indeed every of our partners, all the interested entities, to provide us with a non-paper, so-called non-paper, basically setting out the large lines of what the respective service or other component of Copernicus plans to do for these 7 years, and in order to have to be able to consolidate that and to summarize it and to communicate within our hierarchy with the cabinet commissioner and so on and so forth. So I think this, I took these 2 minutes maybe to outline a bit what is behind your first bullet point, Laurence.
Thank you. Thank you so much, Hugo. So you have understood that we have started this process, and in parallel, we have also started a process of consultation of the member states. And with C3S, so at the ECMWF level, you know that ECMWF is a designated and trusted entity for CAMS and C3S, so the climate services. So with C3S, we have organized bilateral meetings with some countries. It was not possible to visit all the countries, so we have visited actually 9 countries to discuss the potential evolutions and also the ideas that we had, and also listen to the member states' priorities. And after that, in April, it was at the beginning of April, when we celebrated the 50th anniversary, the 50th anniversary of ECMWF. It was a full week of seminar in Bonn, and during this week, we have organized with C3S a workshop to discuss more in depth some aspects of the exchanges that we had with the member states. So those aspects, I think that there were 4 main points that the member states wanted to discuss more in depth. Use of AI/ML. We have talked a lot about use of AI/ML during those 2 days. Improved resolution for the services, inter-services collaboration, and of course, because we were C3S and CAMS, collaboration between climate and atmospheric composition services, and policy support, also to better serve policy support, and joint communication. Joint communication between the Copernicus level, so the interested entities level, and the national experts. And so we have discussed these aspects, and I will just give few insights, picking up few ideas that have been discussed during those process, just to give you a teaser of the ideas for the future. So first, an important thing, you know very well this scheme. This is the current CAMS scheme, how it is organized with all those boxes, with various components of the Copernicus Atmosphere Service, various components, and also cross-cutting components. And what everybody agreed is that finally there is nothing to take out in those boxes, and this scheme is more or less suitable for the user's needs. So there is actually, this is something that has been agreed by everyone. There is no need to change this structure. Of course, there are things to be improved, and we will discuss about that, to be further developed, but the structure as a whole, it's fine. Also, we get very positive feedback about the user engagement strategy that we have implemented, that is based on the National Collaboration Program, but also on the hubs, and also on our training strategy, sharing knowledge, and things like that. So that's the first point. The other point are what are the areas for improvement under Copernicus 3? Certainly, the idea is really to develop innovative, cutting-edge science to better serve the user's need with more accurate and reliable global and regional products. So that's it's obvious, but that's an important point. Maximizing use of satellite observations, since this is something that we've discussed also during this assembly in the coming years. Already now, but in the coming years, there will be more and more opportunity to use Earth observation. AI/ML is certainly a game changer, and this is something that will have to be considered for the future. What relates to observation-based emission work and CO2 MVS that we have discussed this morning. So it will be implemented, and how will it evolve to support in a better way the policy needs. So this is something to consider. and talking again about policy issue, co-design of policy products applications with the national experts. So this is something that really has been raised during our conversation, and those topics certainly will drive the strategy for the future. So if we go a bit more in depth regarding those considerations, we've said, and this has been said also at the beginning of the meeting by the colleagues, the representatives from DG Environment, DG Clima, there is really high expectations regarding the Copernicus services, not only in CAMS, but of course, CAMS, this is very much related to air quality policy, energy policy, climate policy. So there is a need to support the policy processes. And when you talk about policy processes, you talk about some sensitive aspects that relates to the regulation. And it means that we will have some obligations in terms of operational services to be sure that what we provide is the best estimate, the best approach that we can provide to support the policy, the policy application, that what we will provide can be challenged, will be transparent enough to have comparable approach of, for instance, the relevance, the efficiency of the mitigation strategy. So it's very important. It will be very important for us to work on the accuracy, the reliability, the transparency of the product. We've talked about the quantification of uncertainties, and it was in several presentations how to deal with uncertainty. This is not something easy for policymakers, because policymakers actually don't like uncertainties, so that's since this is something to cope with. Operationalization and easy access to the data, and bespoke product application. This is what will be needed to be able to fit with expectations of the policymakers. But Hugo also mentioned that we are talking about the competitiveness fund. So it's also important to have that in mind, that what will be developed under Copernicus will serve also these EU ambitions, and to ensure sustainability, competitiveness, improvement of performance, and be at the top level of the performance is also a must. So this is something to keep in mind. And we have some assets to deal with that, with access to wonderful data sets, thanks to Earth observation, AIML, the possibility to work all together, this community, to co-design products. So here there is really a big role for what relates to NCP and to KCO and knowledge management. So that's those only very big idea. If we go a bit more into detail with concrete example, talking about maximizing use of Earth observation, of course, we talk about the Copernicus missions, the Sentinels-1, CO2M, the Copernicus contributing missions, but also the other missions that are also worth to consider. So we've talked about several of them. Just a few examples: CAMS, TEMPO, for the geostationary parts, microcarb, GOSAT-GW, the Japanese one, YASI-NG, 3MI, and certainly other commercial missions, even if there are some let's say, data management aspects to consider. Maybe more in situ observation. So you've understood that in situ networks are used with data to be assimilated in the products, but also to be used for verification, validation of the products. But maybe we should expand, we should consider how to expand use of in situ observation also in the products themselves, from low-cost sensors to super size. So we have a large range of observations to consider, not with the same quality, not with the same performance, sure, so it will be a challenge to think about the way to develop this integrated framework regarding also the observation, and it echoes very much what Guy was saying yesterday about this integrated framework that we should think about. Increased resolution is something that has been welcomed by the member states for the near real-time activities, reanalysis at the global scale, at the regional scale. So here are some ideas that we have in mind, but nothing set in the stone. Uptake of research project results. It was good yesterday to see what is in preparation, and once again the nice results that we will have already at the end of this year, but in the coming years, and that could help in improving the capacities of our model with expanded numerical prioritization, new deposition products, some work on uncertainties. This will be also part of the COP3 strategies. Exploring the potential of AI/ML, we've said that AFS Compo is already on track, so that's the point, but a lot, of course, remain to be done in all CAMS areas, and in the presentations that you had this morning, some examples have been done, but we should go a step forward also to meet the user's need and to be able to, for instance, prepare, I would say, more ambitious products regarding forecast. With yesterday for AFS Compo, we are talking about 10 days forecast, but also historical, very long historical data set, consistent historical data set. This is something that is requested by many users for the past and for the future. It's true that there are also some requests to be able to play with scenario, to provide some information based on future scenario. And to do that, this is of course very expensive, and you need certainly new tools. Full operational implementation of CO2 emissions. This is completely obvious, but certainly expansion of the capacity of this system based on new data, commercial missions, Copernicus contributing missions, and also expansion of the approach. This approach, which is really focused on the EU and international EU regulations and international agreement. Expanding that to other pollutants like NOx or ammonia, which are quite sensitive for EU regulations, which leads to the idea that it will be important to think about what products should be developed in support to these monitoring, reporting, and verification processes. Further development of policy integrated tool to support the implementation at the member states level of the EU regulation. This is something that has been said several times during our exchanges. And once again, strong engagements with the users in the member states, elaborating on the success of the NCPs, thinking about how co-design tailored policy products, and also working on joint communication between the European level and the more national level. And those are some items that have been discussed during the exchanges that we had, that echo also very much the ideas, the very high-level ideas that we have started to discuss as priorities. And of course, this is just the beginning of the process, so we will be happy to hear also from you. Of course, we will continue to work on that. And maybe last word for you, Hugo?
Yes, maybe you can still go back.
Yes, please.
Thank you. So, thank you very much for this. I think I just wanted maybe to add a few points here as well, in particular on the aspect of harmonization and cooperation between the various components of the Copernicus program. So I think what still needs as well some reflection and possibly maybe some upgrades here and there is in general the aspect of data access. So we have done a lot. We have improved, I think, considerably already the situation with respect to Copernicus 1. So we have VKO, we have CDSE, and so on and so forth. but we would very much like, in particular, in view of the arrival of these automated processing for AI and machine learning, that really we are in a situation that all the data we are producing and we are providing is really easily as well usable for these type of applications, these type of algorithms, and that is not today not completely the case, at least not if you look across various services. So here we would continue our work to get really a more federated data space between the services, EUMETSAT, ESA, to even more facilitate this process. This will, maybe I should say that here as well, this will clearly not mean that kind of this data is going somewhere else or so. It's supposed that that the entity who is producing the data, who has the knowledge about the data, will continue to kind of maintain this data, to evolve it, to make sure it's correct. It's simply that basically the I would say the limits towards the next next data space should be really very low. One very much visible thing for that is we would very much like to see to develop some, in one way or the other, a kind of single logon and joint user management for Copernicus. That goes a bit with the previous point. I would like briefly to mention as well, again, the concept of the thematic hubs. So that's something where we are still reflecting together with service entities how this might be evolved in order to, I would say, solidify this approach and make sure it is not hampered or limited by lack of support or lack of funding. Yes, similarly, we would like to see as well that these NCPs absolutely continue. That's a very high success story. No, so you mentioned it here on your last bullet point. But as well there that somehow the terminology between the services is a bit aligned and so on and so forth on that, so that, I don't know, what is a demonstrator for CAMS is somehow recognizable with a demonstrator for land service or something. Yeah, that's a couple of considerations here. So these are more horizontal and should not kind of interfere with what you have said before. No? Can you move? Yeah. So now I would like to say a bit about the programmatic context now. So I think the most important information on this slide is the URL you can see there. So you will receive the slides, I think, soon after the meeting. So you can go on this site basically to have a look in detail at this MFF package I mentioned in the beginning. Here is one detail of this, or one element of this is here the European Competitiveness Fund. There's here the proposed or the draft regulation as proposed by the European Commission. You can download this file and look at it. It's I don't know, about 100 pages or something, and there are a couple of paragraphs as well about space. There's one article about Copernicus. So you will hopefully recognize a bit what is in the current space regulation there as well. But clearly, the trend of this new MFF is towards consolidation of legal instruments. So Copernicus 1 was a standalone regulation. Copernicus 2 was part of a space regulation. And now even more, all the space topics, the defense programs, as well as resilience, security program, all this is now one area in this competitiveness fund. There are other areas, 3 other areas, basically for digital, whereas as well what is today the Digital Europe program. And there's another area on health, bioeconomy, biotechnology stuff, and the fourth one. And so all this is now one tool, closely associated with Horizon Europe. And so yeah, this is, and that's a level on which these budgets are at the moment discussed or described in this package. So you will not yet find there a Copernicus budget line or even a CAMS budget line. That's we are here now seeing this at the level of this area I mentioned before. So there is for space, defense, and this security and resilience. So there's a total of 131 billion allocated, but the finer, I would say, decomposition of this figure into more details is not yet there. And so even me, I don't know any any figure myself. So that's a bit what I wanted to say here, I think. The purpose of this, I would say, aggregation of programs is, of course, to be efficient, not to have programs which address a bit similar things, similar stakeholders, and work according to different rules, different eligibility, different funding rules, and so on. So this is about very much having basically the same procedure and same rules for all these programs, which are inside this competitiveness fund and as well with Horizon Europe. I think by the way, one side effect of this, or one effect of this, is that we as DEFIS, we will probably get much better control over the space topic of the Horizon Europe than we have it today. So that's maybe much more easier for us then to align really the research calls and that with the operational program now. So I think there was yesterday a question about that from someone, I forgot. Yeah. So thank you.
Right, thank you very much, Laurence and Hugo. So now we can open the floor for questions.
Okay, I have 2 questions. Thank you very much. I think I heard the view of ECMWF, which is very impressive, and I think you have been thinking quite a bit about it. I would like to raise 2 issues related to that. The first one is that I wonder if, in a step further, it wouldn't be possible to be more defining products that are adapted to the need of users. Give you some example. What does the health community really need? What product? What does the oil company that have leaks in their pipeline, what do they need as maybe alert system or these kind of things? What does a mayor need to know what kind of action he should take or she should take to solve the problem that the city has? And so I'm wondering, for example, urban information is becoming more and more important. It might not be on the global scale, but at least on the regional scale, going a bit further. So that's my first point. My second point is that in the life of CAMS, we've been looking at oxygen like ozone, then aerosols, now greenhouse gases. That might evolve also towards new substances. And I can think, for example, of new pollutants. Microplastics is one. Fluorinated species that are used more and more and have a long lifetime. You could think also of the connection between indoor pollution and outdoor pollution with a lot of the products now that are coming from indoor or in-city use for washing, for cleaning, for painting, for cosmetic, if I could say, all these kind of things. So there might be new topics that are coming up. So I was just suggesting that you think about those.
Thank you. Thank you very much, Guy, for your comments. Yes, regarding the products, application that are really focused on our users' needs, this is, yes, what is a bit behind this bespoke application or tailor-made applications, really listening to what are the needs. And because it's true that all CAMS data sets are available, and we put that in our data stores, but sometimes this is not very easy to use for a community of users. So this is the reason why we have also the hubs. We have various initiatives to support that, but certainly it should expand in the future. And yes, chemicals of emerging concerns, for instance, this is microplastic, definitely, PFAS, definitely, pesticides, so persistent substances. It will be certainly looking at the environmental regulations, certainly the focal point for future regulations, because we know that we will have serious health and environmental issues with those pollutants. But we need data. We need observation data, emission data, and things like that. So we have to certainly to pave the road and to be ready to uptake. But yes, it will be a common effort, certainly. So, yes, go, please.
Yes, thanks. Thanks for the question. I think I fully understand where this question is coming from, so that's highly appreciated. But we need to keep in mind as well that there's a full value chain of Copernicus or in the Copernicus environment, and the services cover a certain part of this value chain, but not necessarily all the I would say last mile things where you have to tailor things to country-specific aspects, to community-specific aspects, and so on and so forth. So, for instance, if we evaluate or have to assess our program ourselves, like Copernicus, we asked what is the European value of the value at European level for this, and could this have been done at a lower level? No? That's this famous principle of subsidiarity. And for this downstream application, I think, frankly, that there are other smaller, more agile actors which are maybe in a better position to serve these users than an EU program. No? And so there's a link between your question as well and what Edouard was explaining yesterday, that indeed there should be for instance, service providers, consultant companies, and so on, should fill this gap that you have described. No?
Okay, thank you. Leonard.
Yeah, first, thank you for sharing your views on CAMS 3 and how it is evolving. And also, thank you very much, Hugo, for this last comment, because it's very important in CAMS that we are working towards the policy that is already existing, which is the air quality directives, where the subsidiarity principle is very clear, and where the service has a role, the downstream services have a role, and the cities have a role. The national activities are important, and we cannot go all the way through because of this subsidiarity principle. So when we are always talking about the urban areas, this is the responsibility of the countries. And many of you are here as countries, and then that is another role, but it's not at the service. And I think this is very important that we understand, because it's in the regulation. Microplastics is not yet in the regulations, but heavy metals are there. And it's also the VIPs. And I haven't heard that into this part, so I wonder, with that clear drive from the legislation, where we are already asking for heavy metals and for the VIPs, can we do something with that? How do we put it into the CAMS 3? And also another part that is there, which is very interesting, it's there in your line, it's saying, how do we cooperate with the other services? But one thing that is very important in both the Air Quality Directive and the NEC Directive is the link to ecosystems and biodiversity. Also, you mentioned yesterday how much the biogenic are getting more and more important. So how is the links really, especially between the Copernicus Atmospheric Service and the Copernicus Land Monitoring Service? Because this is the part where the biodiversity is important, the bioeconomy will come in. So analyzing these parts and maybe putting them a bit more clear for the CAMS 3, it would be something maybe to think about, and I wonder what are your plans on that?
Just, Leonor, yes, you're right on this last point. This is also what is beyond, but I know that you know, the fact that we are working on deposition products, new deposition products, and this is exactly to be able to have useful and reliable tools to support what relates to protection of ecosystems and biodiversity management and things like that. And we, ESA organized, I think, when was it, at the beginning of the year, this symposium, this workshop on biodiversity and use of Earth observation and on biodiversity. And the European Commission has set up a specific session on Copernicus services and how they could serve the biodiversity questions. And all the services were on the stage to work together and to be able to think about how we could better collaborate to deal with those objectives. That's a very good point. And yes, and you mentioned heavy metals. I also have what relates to, you mentioned BAP as well, and as a whole, pollutant organic persistent, because this is also what I think that will be really, really sensitive in the future. Yeah. And there is a regulation.
Maybe to add, the original idea of the hubs was also to see how we can bring services more together on specific thematic areas. And in this phase, it's experimental. There's clearly not sufficient funding to really explore this to its full extent. But if there's really a need for those things, then we really need to consider this carefully, how we would do this and what sort of effort this would take, what are the resources, and how can we indeed bring the different services more together, apart from just the current specific cases where there is interaction between the different services. Ilse.
Yeah, I'm not sure this is the right forum, but I'll give it a try. So I'm sort of struggling. For sure, supposed to go to space agencies, and I raised the issue of the fact that we need to validate maybe different products from the satellite observations. They're going to higher spatial resolution, as we know, facility scale, and some of them are only giving you emissions because they're not meant to give us full concentration fields. This is not what they are aiming for. So I think that is, I was wondering if, in addition to the space agencies and others that have a role to play in validating these products, I was wondering to what extent there may be a role for CAMS as well, or opportunity with all the tools and blah, blah. Yeah.
So you're referring specifically to
I'm referring to the fact that we are getting a lot of satellite observations,
yes,
as we know, and some of those are really at very high spatial scales, and that some of those, in addition, only basically are not oriented to give us good concentration fields. They're just oriented to give us good emissions. Yes. And so we should validate these emissions. Yes. And again, I'm not saying CAMS is the first place to look for that validation. It should be with, I think, space agencies and others. But the question is, there may be a role for CAMS to play here. Because it's really a different type of data product that we're getting, both in resolution and in what it's actually giving you.
Yes. No, I think you're right, and that's certainly ambition we have to basically create, to some extent, a benchmark system that can support other activities and their interpretation. Of course, we are, some things within CAMS are quite mature, other things like emission monitoring we're still building up, but it's certainly an ambition we have to as part of a publicly funded EU program, to provide the data that can also be a reference for all kinds of other activities. And certainly, if you look at the greenhouse gases within the whole transparency framework of the Paris Agreement, this is clear. We need to provide that one way or another. And that's also where we are working hard with WMO within the new Global Greenhouse Gas Watch well, we try to set up. It's not going without any challenges, but let's see where we can get. But that we also have this international collaboration there currently with US partners, with Japanese partners, Chinese, to make sure that as a global community we know what we're looking at, and we can make sure things are consistent.
And validated.
And validated. Yes. No, you're right. That should be part. I mean, at least we need to make sure we validate our products correctly, so then it can be used. Yeah. Other questions? Any wishes for the next phase of CAMS? Johannes.
You also mentioned the importance of the in situ data, and we noticed that some of the international sort of networks for in situ data are sort of declining, or they don't measure so often anymore. I mentioned ozone sondes, and we also understood that the Aeronet network is maybe has complicated situations ahead of them. Is there anything that Copernicus could maybe do on the international scale to keep these in situ networks going?
Who's going to answer? Because I'm fully supportive of this question, but I don't know the answer. No, I mean, I can start with. So we all agree in situ data is important, also for space agencies. Actually, within the European networks, we've always struggled with what should be funded through Copernicus and what through national funding. And member states don't always agree there, so that has proven to be difficult. But you're right, now there is also global networks that are at risk, and how do we keep this alive? And I don't have the answer. I don't know if Hugo has anything to say.
This is in the roadmap. I think that, yes, in situ networks, they are on our roadmaps in cases. It's true that we are also in this strange situation, and you've mentioned UNS, Aeronet, and yes. bit frightening situation, worrying situation at least, but sure that what relates to in situ at the global scale should be part of the strategy, and certainly expansion of the data sets that we should be able to manage. Yeah. Also, in the idea that we also have to expand the capacity of the global system.
Yeah, maybe we can add that within Copernicus there is a European Environment Agency who is in charge of the in situ component, or basically sort of coordinating in situ data access between the services, space component, and so on. Amongst which are, of course, as well international networks and so on. And so they have started and are basically now in the process to make an assessment of these changes you are maybe hinting at. I'm sorry, I can absolutely not see you. I'm completely blinded by this spot over there. So that to try to see a bit what we can do at Copernicus level to, I would say, maybe improve a bit the situation. On the other hand, it's very clear that as Copernicus we cannot fix everything that maybe is damaged by this change in policy from certain parties internationally. No? So I mean, there are quite a lot of requests in the sense that we are getting at the moment, so I won't go into detail here now, but so clearly there is an issue, but I'm not sure that we alone can fix it. No, we can try to limit the damage, I would say, but we cannot completely fix it or step into everything that that US has been doing so far. No?
Yes. Anything else? No, everything clear. Okay. Sorry? Yeah. Then we conclude this part. I think, well, we were close to the end of the session anyway. So I hope this was informative. Clearly still, well, there's lots of ideas, but there's also question marks, obviously, related to the funding. This is not unusual. We had exactly the same process last time and also the first time. So we know how it works, but yeah, let's see where in the end the whole program ends up, and hopefully we can fulfill as many of the ambitious as we have as possible. So thank you to Laurence and Hugo for the information. And then we'll move to the final session of this General Assembly, the closing. So I'd like to invite Maria as well. You are on the agenda. No, you're not.
Yes.
Great. It's a great tool for short Scandinavian people. Okay, so here we are at the end of another successful General Assembly. Many thanks to the organizers, the technical teams, the communication, the management, the local host, the speakers, and of course to all of the participants. The short conclusion is that CAMS is growing and evolving. In numbers of staff, of contracts and users, in products and service elements, and in outreach. It's good to see it all coming together here on stage, in the posters and side events, and not least in the room among the participants. Once again, meeting in person and having these informal chats in the coffee breaks or in fashionable halls in Prague Old Town is really, really invaluable. Personally, I have gotten a lot of input and ideas to work on for the next year that I'm quite sure that I wouldn't have received per email or been asked in a meeting. In addition, I've gotten a quick language course in Czech, recommendations for TV series, and updates on people's families and pets. And this is the beauty of meeting each other once a year, that we actually get to know each other and form great working relationships by lowering the threshold to contact each other and ask questions, knowing whom to involve in different processes. A lot of things that ultimately leads to a more comprehensive end product and service. We are entering the final years of this Copernicus period, and we have just heard about some future plans and outlooks. But for this period, we now see the paragraphs of the contribution agreement materializing. Many things that only existed on paper a few years ago exist now in real life. Examples are the National Collaboration Program, the thematic hubs, though still evolving, the greenhouse gas emission monitoring service ramp-up, for example, with the Methane Hotspot Explorer, in addition to all of the developments done in the core service elements, of course, and the preparations for data uptake of upcoming missions, such as the CO2M, and the newly launched missions Sentinel-4, 5, and Microcarb, for example. So CAMS is a big system. It's still expanding, and it's also part of an even larger system, the Copernicus ecosystem, together with 5 other Copernicus services, with the space segment, the in situ component, and all of the interested entities operating all of these different parts of the system. ESA, EUMETSAT, USPA, EAA, Mercator, Ocean, JRC. I hope I didn't forget anyone. It is complex, and it does require a lot of coordination and collaboration. But it makes Copernicus a complete Earth observation system, from measurements and observations to actionable information. This includes specifications and development of satellite missions, research projects, development and provision of operational services, and information both for the general public and decision-making, and more. And Copernicus has users in all steps of this value chain, from scientific users, national services, media, students, policymakers, you name it. Of course, in a big ecosystem, some parts can always be better connected. For example, the uptake of research projects outside of Horizon service evolution calls, as just mentioned, like the ESA CCIs into the operational services. This is something that we can work on enhancing and coordinating in the time to come. Then the input in Copernicus is not a straight line, but it's a feedback loop with policy input and signals feeding into the services and development. And as you heard in the beginning of this General Assembly, Copernicus products and tools are appreciated by the policy DGs and used for policy implementation and to follow up on directives and regulations. I really hope that you take that message, that your work is used and appreciated in the policy domain, and it has an impact. So on that note, I would like to thank you again for this year's General Assembly, encourage you to keep up the good work, and See you next time.
Thank you so much, Maria, for those nice words and nice conclusions. So now it's time to end. So many thanks to all of you for your active participation to this General Assembly, but also for all the work that you do to support the development of CAMS. And I think that, yes, we've done a good job. So many thanks to all of you. Regarding this assembly, I would like also to thank Charles University and in particular, Katharina, many thanks for your help, really. In organizing this successful event. I would like also to thank our colleagues from the Copernicus CAMS unit and Francesca, who organized everything with the colleagues from Adria Congress. So many thanks for this work. I think that everything went well and everybody appreciated a lot. Many thanks to all of you. And with that, so we've taken notes of things. We have our to-do list. We have our to-do list. And so I hope that you will have a safe trip back home. Hope to see you next year, certainly for some of you before. And enjoy your weekend now. So we've done a good work. So thank you very much and see you soon. And maybe Rich, I want to say goodbye, and goodbye. See you.